I've heard the idea many times late at night, in documentaries, in quiet conversations, in half-serious theories passed around online. That our universe may not be the first one. That before our stars ever learned to burn steadily, before galaxies like the Milky Way existed, there might have been an earlier universe. It had its own matter, its own time, its own long history. Stars formed, galaxies grew, perhaps even civilizations rose far enough to believe their universe would last forever. And then, at some point, it ended. Not just life, not just a world. The entire cosmic framework came apart. And yet, according to the story, something followed. A rebuilding. New matter, new space, new time, another beginning, and maybe, much later, another ending. Not as a single catastrophe, but as a repeating pattern. Formation, complexity, disappearance. Again and again. Most people hear this and treat it as myth, a comforting idea, dramatic, impossible to verify. What surprised me was discovering that this idea doesn't belong only to speculation. In the final book of the Bible, the book of Revelation, there is a quiet, striking line. Then I saw a new heaven and a new earth, for the first heaven and the first earth had passed away. It isn't written as physics, but the structure is unmistakable. An ending, followed by something new. And here is where things become unsettling. Modern cosmology, working not with prophecy but with observation and equations, has reached a point where it must ask a similar question. When you follow what we know about expansion, entropy, dark energy, and time far enough into the future, you are forced to confront something both simple and deeply uncomfortable. Does the universe actually end? If it does, what kind of ending is it? Slow and cold, sudden and violent, or a collapse back into itself? And if there is something after, what could after even mean? When time itself may no longer function the way we understand it. Today, we're not looking for certainty. We're looking for the most honest answer science can currently give, one that doesn't declare the mystery solved, but finally shows you why the question refuses to go away. For a question as large as the end of the universe to even exist, something much quieter had to happen first. We had to notice that the cosmos itself is capable of change. At the beginning of the 20th century, most scientists still imagined the opposite. The universe, in their minds, was essentially a grand, static backdrop. Stars might be born and die, nebulae might shift, but the overall stage was thought to be timeless, eternal. The same yesterday, today, and forever. It felt obvious in the way that deep assumptions often do. If you look up at the night sky over a single human lifetime, it does not seem to be doing very much. Even Albert Einstein, when he first wrote down the equations of general relativity, carried this intuition with him. His equations, left to themselves, suggested that the universe should either be expanding or contracting. Space, under the influence of gravity, wanted to move. That result looked wrong. At the time, there was no evidence that the universe as a whole was changing. So he added an extra term, something he called the cosmological constant, a kind of finely tuned cosmic pressure that could balance gravity and hold the universe in place. It was a mathematical way of saying, stay still. Dizi for pedos. We sometimes tell that story as a joke at Einstein's expense, but it is worth pausing with it. One of the sharpest minds in human history looked at his own equations and decided to bend them to protect an intuition about the universe, that it should not have a story, that it should simply be. The night sky, after all, encouraged that belief. For someone standing on Earth, the stars rise and set, but they do not appear to be carried away. The constellations handed down from ancient myth still roughly match the patterns we see now. The idea of a universe with a beginning and an end belonged mostly to theology and philosophy, not to physics. Then, in the late 1920s, a telescope on a mountain above Los Angeles began to whisper something else. On a clear night in January of 1929, Edwin Hubble and his colleagues at Mount Wilson Observatory were working with photographs of faint smudges in the sky. These smudges had recently been recognized as other galaxies, far beyond the Milky Way. By analyzing the light from those galaxies, Hubble could measure how much their spectral lines were shifted toward the red end of the spectrum. That redshift, in turn, told him how fast they were moving away. One galaxy after another, the pattern emerged. The farther a galaxy was, the faster it receded. Not randomly, not chaotically, but in a smooth relation. It was as if space itself were stretching, carrying galaxies apart like dots on an inflating balloon. In that data, the universe suddenly acquired a past and a future. If everything is moving apart today, then at some earlier time it must have been closer together. And if expansion continues, the distances between galaxies will grow. The cosmos, which had been treated as a fixed arena, revealed itself as a process. When Hubble published his results, the full emotional weight of this shift did not land at once. Debates continued. Alternative explanations were explored, yet slowly. The static universe gave way to an expanding one. The stage itself was moving. Still, it was only the first step. Knowing that the universe is expanding does not, by itself, tell you how it began or how it will end. For that, we needed another piece of evidence, and it arrived in a far less glamorous way. In May of 1965, two radio astronomers, Arno Penzias and Robert Wilson, were working with a large antenna in New Jersey. They were not hunting for the origin of the universe. They were trying to reduce noise. Their instrument picked up a persistent hiss, a background signal that did not go away no matter where they pointed the antenna. They cleaned out pigeon droppings from the dish. They checked every possible source of interference they could think of. The hiss remained. Eventually, through conversations with nearby theorists, it became clear. They had stumbled onto a relic from the early universe, a bath of microwave radiation filling space in every direction. What they were hearing, in the language of radio noise, was the afterglow of a hot, dense state billions of years in the past. This cosmic microwave background, as it came to be called, turned the vague idea of a beginning into something much more concrete. The universe had once been far hotter, far denser, and far more uniform than it is now. The expansion that Hubble inferred from galaxy motions was not just a local trend. It was the widening of a cosmos that had started in an almost unimaginably compressed state. Taken together, these discoveries gave the universe a visible arc. A hot, dense beginning, an ongoing expansion, structures forming over time. For the first time, it made sense to ask, in a scientific way, not only how did this start, but also where is this heading? For several decades, that question was framed in fairly simple terms. If gravity wins, the expansion could slow, halt, and reverse, leading to a future collapse, often called the Big Crunch. If the expansion wins, the universe might drift outward forever, galaxies growing more distant but never returning. Within that framework, cosmologists collected measurements, trying to weigh the universe. How much matter did it contain? And would that matter be enough to pull everything back? The story could have stayed like that. Two broad possibilities. One fiery ending. One endless cooling. Then, near the end of the 20th century, something deeply unexpected slipped in through the light of dying stars. In the 1990s, two teams of astronomers set out to use a particular kind of exploding star, called a type Ia supernova, as a standard candle. These supernovae reach nearly the same peak brightness wherever they occur. So, by comparing how bright they appear to us, we can estimate how far away they are. The idea was elegant. Map out the distances and redshifts of these explosions in distant galaxies, and you can reconstruct how the expansion of the universe has changed over time. In January of 1998, the teams, known as the Supernova Cosmology Project and the High Z Supernova Search Team, presented their results. The distant supernovae they had observed were dimmer than expected. That dimness meant they were farther away than the prevailing models predicted. The inescapable conclusion was that the expansion of the universe was not slowing down under gravity's pull. It was speeding up. Something, filling space itself, was pushing galaxies apart more and more strongly over time. The cosmos was not just expanding, it was accelerating. Later that year, a major scientific journal named this discovery the breakthrough of the year. Outside the community, the news filtered slowly through documentaries and magazines, often under a phrase that is both accurate and deeply mysterious: dark energy. For many cosmologists, the emotional shock of this result was real. For decades, the great debate had been whether the universe would expand forever or collapse back on itself. The supernova data suggested a third possible fate: a universe whose expansion accelerates without bound, thinning matter out faster and faster, steering the cosmos toward a very different kind of ending. Suddenly, the old diagrams in textbooks, with curves showing expansion slowing to a stop and then reversing, began to look outdated. New diagrams appeared, lines that bent upward, representing expansion that accelerates. The traditional image of a dramatic big crunch started sharing space with a more unsettling possibility: a slow, cold fade, sometimes called the Big Freeze or the heat death of the universe. In cultural terms, this shift is almost comically recent. The idea that the universe might end, not in a catastrophic collapse back into fire, but in a long, quiet approach to thermodynamic exhaustion, is only a little older than the era of home internet connections. Many people alive today grew up with one version of the universe's future in school and then discovered, in adulthood, that the script had been redrafted. You can see the confusion in the way popular shows talk about it. One documentary from the early 2000s might still mention the possibility of a recollapsing universe as though it were a strong contender. A later video, scrolling through a timeline of cosmic doom, might quietly assume that acceleration, and with it heat death, is the default. Generations of students and late-night viewers have been trying to update their mental models on the fly. And yet, when this new picture leaks into everyday conversation, it often carries a strange emotional double edge. Imagine a long-form science video where the host, in a relaxed tone, mentions that under some models, the universe could drift toward near-complete emptiness over a timescale of roughly 10 to the power of 100 years. The number is so large that it barely feels real. Somewhere in the comments, someone writes, half joking, "Why does this make me more calm than anxious?" Part of the answer is that the timescales are so vast that they dissolve personal fear. A heat death that takes 10 to the power of 100 years to fully unfold is not a threat to anyone's weekend plans. But there is something else at work too. The idea that the universe has a long, drawn-out future, rather than an imminent fiery collapse, subtly changes how we imagine our place in it. We are not perched at the brink of a final explosion. We are somewhere in the middle of a very long, very slow story. Of course, nothing about the data says that the universe must end in this way. The discovery of accelerated expansion tells us that right now, the universe's fabric is being pushed apart by something like dark energy. It does not guarantee that this something will behave the same way forever. It does not guarantee that there is no trapdoor event waiting in the equations. What it does is force us to reframe the question. If the cosmos is expanding and that expansion is accelerating, then the future is not a simple extrapolation of the past. Distances that are already large will grow faster. Galaxies that are currently within view may one day drift beyond our cosmic horizon, effectively vanishing from any possible contact. The night sky itself becomes a changing thing, not just in the slow motion of stellar evolution, but in the very arrangement of what can be seen. So we arrive at three questions that will quietly sit under everything that follows. First, does this data actually mean the universe must end in any meaningful sense of that word? An expanding universe with accelerating separation might still exist forever in a bare mathematical way. But does it run out of the capacity for new events, new structures, new stories? Second, if the universe does end, how does this expansion write the shape of that ending? Does it stretch things thinner and thinner until differences disappear? Does it tip the cosmos toward a catastrophic tearing? Does it somehow reverse and return all matter to a final, compressed state? Third, if there is something that could be called an after, what could that possibly mean? When time itself is part of the system under discussion? In a heat death where nothing changes, does after lose its meaning? In a bounce or a new cycle? Does after belong to another universe entirely, sealed off from ours? These are not questions that can be settled by a single experiment or a single equation. They sit at the intersection of observation, theory, and the limits of what we can reasonably project. Still, there is a line you can draw through the 20th century into the present and see something clear. A century ago, the universe was often imagined as static, eternal, and largely indifferent to our talk of beginnings and endings. Then, Hubble's widening galaxies, Penzias and Wilson's microwave hiss, and the distant, dim supernovae of the 1990s together forced a different view. The cosmos, we now know, has a history. It once was denser and hotter. It is expanding today. The rate of that expansion is changing. When we ask how it will end, we are not imposing drama on an indifferent backdrop. We are following the trajectory of a story that has already surprised us more than once. You could say that there was a kind of long, collective night in which this realization settled in. Not a single evening, but a span of decades in which telescopes, equations, and human stubbornness gradually replaced a static stage with a moving narrative. By the time that night was over, we had learned to see the universe as something with a beginning, a middle, and some kind of future arc. Even if the last chapter is still written in faint pencil marks, we are only just learning how to read. Once you see the universe as a story, not just a setting, a new discomfort arrives quietly in the background. Stories, almost by definition, have endings. The word itself sounds simple. For a person, an ending is bitterly concrete. A heart stops. Breathing halts. There is a before and an after, and the line between them feels sharp. But when we try to lift that same word and place it over a universe, it starts to slip through our fingers. What exactly would have to happen for us to say, with a straight face, that the universe is over? Imagine, for a moment, that every star in the sky has gone out. No more suns, no more fusion. Every galaxy has turned into a faint swarm of cold embers and dark remnants. Space keeps expanding. The clock keeps ticking. Physical laws continue to hold. But there is nothing left that looks like a bright, living cosmos. Would you call that an end, or is it simply a very long, very boring middle? Part of the confusion comes from the fact that our everyday sense of endings is shaped by abrupt change. A falling glass shatters. A film cuts to black. A book closes. We are used to endings that arrive with a clearly audible click. Physics, especially when we stretch it to cosmic scales, offers a different palette. Some endings are crashes. Others are more like asymptotes. You never quite see the final step, but the possibility of anything new gradually thins out. Cosmologists sometimes draw that distinction by thinking in terms of the stage itself. There are what you might call hard endings, where space-time as a whole breaks or collapses. In a big crunch, the expansion of the universe reverses, and everything that was once flung outward falls back together into an extremely dense state. In a big rip, if the mysterious dark energy were to become even more repulsive over time, expansion could speed up so violently that not only galaxies and stars, but planets, molecules, and eventually atoms themselves would be torn apart. In both of these pictures, something about the fabric of reality reaches a violent limit. Then there are soft endings. In these, the mathematical arena of space-time carries on, but the content inside it loses the ability to rearrange itself in interesting ways. Heat death is the classic example. The universe expands forever, stars burn through their fuel, matter decays or drifts apart, and temperature differences even out until, in a practical sense, nothing much happens anymore. There is no single cosmic bang of closure. Instead, the capacity for change slowly evaporates. A simple way to frame this is to think of two different movie failures. In the first, you are watching a film, and just before the final scene, the screen suddenly goes black. The projector dies. The story stops mid-motion. That is a crash. It feels unfinished, even if you know it is over. In the second, the movie keeps running, but something has gone wrong in the playback. The same frame is repeated again and again. The sound is a flat hum. Time passes. Images flicker. Technically, the film has not ended. The reel is still turning. But for you, as a viewer, there is nothing left to watch. No new information. No change. In that sense, the story has ended, even though the mechanism continues. Heat death is closer to the second kind. The universe, as an abstract physical system, may persist indefinitely. Equations continue to apply. If you could somehow stand outside and look at the whole thing from a timeless vantage point, there would still be something there. But from the inside, from the point of view of any possible observer, the story has frozen. To describe this more carefully, physicists summon a quiet but implacable character: the second law of thermodynamics. In ordinary terms, it says that in a closed system, entropy tends to increase. Entropy is often associated with disorder, but a more careful way to think about it is as a measure of how many microscopic arrangements correspond to the same macroscopic situation. Higher entropy means there are more ways for the underlying pieces to be shuffled, while everything looks roughly the same from far away. When physicists talk about the end of the universe, they are not usually imagining a magical disappearance of matter or some cinematic vanishing act. They are asking a cooler, more technical question. Will there eventually be no free energy left to do work? No gradients to exploit? No way to build engines, living cells, stars, or thought processes that feed on differences? In that language, an ending is not the moment when everything ceases to exist. It is the point where existence no longer supports the kind of organized processes that make stories possible. What is striking is that these worries about cosmic exhaustion did not begin with modern cosmology. Long before we had precise measurements of the expansion of the universe, long before the cosmic microwave background was discovered, 19th century physicists were already haunted by the implications of the second law. Rudolf Clausius, one of the founders of thermodynamics, helped formulate the concept of entropy in the context of heat engines. Lord Kelvin, thinking about the fate of the sun and the limits of steam technology, pushed the idea further. If every energy transformation in an isolated system increases entropy, and if the universe as a whole can be treated as such a system, then does it not follow that, given enough time, all temperature differences will eventually disappear? That no more useful work will be possible anywhere? From their vantage point, the nightmare did not come from galaxies or black holes, which were not yet central to physics. It came from steam engines and cooling iron. They extrapolated from boilers and pistons to the sky. This idea of a universal heat death spilled out beyond physics. Philosophers and writers in the late 19th and early 20th centuries wrestled with it. If not only individuals and civilizations, but the cosmos itself tends toward a state where nothing new can occur. What does that do to concepts like progress and purpose? Some thinkers found it depressing, as if the universe were a beautifully written novel, guaranteed to end in blank pages. Others saw in it a kind of tragic grandeur, a recognition that even the grandest structures are temporary. For our purposes, we do not need to follow every branch of that philosophical conversation. We only need to keep one essential point in view. When cosmologists today speak about the possible endings of the universe, they are usually talking about three broad families of scenarios, all of which can be traced back to the interplay between expansion and entropy. The first family is the heat death, or big freeze. In these scenarios, the universe continues to expand forever. Galaxies move farther and farther apart. Star formation gradually shuts down as gas is used up or scattered. Existing stars age and die, leaving behind white dwarfs, neutron stars, and black holes. Over staggering stretches of time, those remnants themselves cool, decay, or evaporate. Temperature differences even out. Eventually, all that remains is a thin mist of particles and low-energy photons spread over an ever-widening space. Nothing dramatic happens at a particular moment, but the ability to generate new complexity fades towards zero. The second family encompasses catastrophic endings. These include the Big Rip, in which a particularly aggressive form of dark energy grows stronger as the universe expands, driving everything apart in a finite time. And the Big Crunch, in which the expansion eventually reverses and everything collapses back into an ultra-dense state. We might also place vacuum decay here, a hypothetical event in which the underlying quantum vacuum of the universe tunnels to a lower energy configuration, changing the laws of physics in a bubble that expands at nearly the speed of light. In each of these cases, there is a kind of crash. The stage itself is altered or destroyed. The third family is cycles and reboots. In these ideas, what looks like an ending from the inside of one cosmic era might be the starting point of another. A crunch transitions to a bounce. A dead, radiation-dominated universe is mathematically reshaped into the seed of a new Big Bang. Brains collide, universes bud off from black holes, aeons hand off to other aeons. These models are more speculative and diverse, but they share a pattern. No single, ultimate ending, but a chain of transformations, possibly without a final stop. It is easy to say these words quickly. Heat, death, rip, crunch, cycle. It is harder to feel what they imply once you connect them to timescales. A human life, if things go well, might span something like 10 to the power of 2 years. The Sun's main sequence lifetime is on the order of 10 to the power of 10 years. Many of the heat-death timelines discussed in cosmology involve durations closer to 10 to the power of 100 years and beyond. These exponents are so large that they push against the limits of imagination. We can say the phrases, we can write down the powers of 10, but we cannot build an intuition that genuinely stretches that far. Strangely, this mismatch can make the whole subject feel less frightening. When a documentary whispers that, in a future so distant it dwarfs the current age of the universe, all stars will be gone and black holes will evaporate, the mind often does something protective with that information. It files it under effectively never. The apocalypse has been postponed to an extent that dissolves urgency. Popular culture tends to lean in the opposite direction. In a film like Interstellar, released in the year 2014, the crisis is local and near. Crops fail. Dust storms rise. Humanity faces the end of habitability on one small planet in one modest solar system. Within a few generations, that scale is visceral. You can imagine your grandchildren breathing that dust. Cosmic endings, by contrast, operate on such enormous spans of time and space that they almost become abstract. It can feel comical to hear the same language of catastrophe used for both. The end of Earth's crops in a few human lifetimes is not the same kind of problem as the fading of all stars over quadrillions of years. And yet, from the point of view of physics, they are connected by the same underlying logic. Finite energy sources, changing conditions, growing entropy. This is why it helps to be precise about what we mean by end. If you say, the universe ends in a heat death, you are not claiming that at some particular Tuesday in the unimaginably far future, everything suddenly ceases to exist. You are saying that, according to our best current models, there comes a time when the universe no longer supports processes that can generate new, large-scale structures or maintain complex, energy-hungry systems. Stars cannot form. Black holes cannot keep feeding. Life, if it persists, is forced into ever more marginal strategies, eventually encountering hard physical limits. If you say, the universe ends in a big rip, you are imagining a more violent horizon. A finite time in which cosmic expansion becomes so extreme that no bound structure can survive. Galaxies unbind, solar systems are torn apart, molecular bonds fail, even atomic nuclei are ripped. Quieter fates, like heat death, leave space-time intact. Rips and crunches question the integrity of space-time itself. And if you say, the universe does not really end, it cycles, you are doing something else again. You are taking the word end and placing it within a larger, perhaps endless framework. The death of our universe is real and final from our perspective. But in a bigger picture, it might be one transition among many. That is not a claim we can currently justify with strong evidence. It is a way of exploring the space of possibilities allowed by equations we only partially understand. Underneath all of this lies a more human question, one that often stays implicit. When we ask, does the universe end? Are we asking about mathematics or about meaning? If the equations describe a universe that continues indefinitely in some barren, high entropy state, then, in a very literal sense, there is no final moment. Time, as a parameter, keeps stretching. But from the perspective of any imaginable observer, there might come a point where no new patterns can form, no new memories can be laid down, no new structures can emerge. Physics would still exist, laws would still operate, yet there would be no narrative in any sense we recognize. So perhaps the sharper way to phrase the question is this: does there come a time when no new stories can happen? A time when the raw material for change has been used up? Gradients have flattened, and the universe, while still there, has lost the ability to surprise even an immortal, patient intelligence? If the answer is yes for any of the scenarios we have sketched, then those scenarios deserve to be called endings, even if they do not involve a clean, finite cut in the flow of time. They mark the boundary beyond which the universe, as a place where things happen in sequence, gives way to something closer to stillness. In the chapters to come, we will move more slowly through each of these possibilities, grounding them in what we actually observe. The fading of starlight, the physics of black holes, the strange pressure of dark energy. For now, it is enough to hold on to this quieter reframing. The end of the universe may not be a single catastrophic instant. It may be the moment, spread over inconceivable stretches of time, when narrative itself becomes impossible. If an ending for the whole universe is really about the fading of stories, then the place to begin is not with galaxies at all, but with something as ordinary as watching something cool down. Picture a cup of coffee sitting on a table. When it is first poured, steam curls up from the surface. The air above it shimmers. You can feel the warmth on your skin from a short distance away. Leave it alone for a while, and the scene quietly changes. The steam thins, then stops. The surface goes still. You touch the mug, and it feels only a little warmer than the room, then not warmer at all. No one announced that anything important was happening, but a small, one-way transformation has taken place. Hot coffee has become lukewarm coffee. Lukewarm coffee has become room temperature coffee. It does not go the other way. The same pattern plays out everywhere. A phone battery, fully charged, slowly drains as you use it during the day. A tidy room gradually attracts dust and clutter. A block of ice on a kitchen counter melts into a puddle that spreads and cools. We do not find puddles of water spontaneously pulling themselves together into neatly carved ice sculptures. We do not find your living space, left alone, becoming cleaner and more organized over time. In all of these small, familiar processes, something is drifting in one preferred direction. That preference is what we mean by an arrow of time. Not the ticking of a clock, which simply marks duration, but the fact that certain transitions happen and their mirror images do not. The physical quantity that tracks this asymmetry is called entropy. For many people, entropy is introduced as disorder, but the word disorder carries emotional baggage, as if the universe were making a moral choice to become messier. In physics, the idea is more neutral. and also more interesting. Imagine you are standing far across the street from a window, looking into a kitchen. From that distance, you cannot see every molecule of air. You see only overall patterns. The coffee cup sits on the table. Perhaps a cat is sleeping in the corner. To you, many different microscopic arrangements of atoms would look exactly the same. The idea behind entropy is to count how many underlying arrangements correspond to the same visible picture. A low-entropy situation is one where there are relatively few microscopic ways to be arranged while still looking the same from far away. A high-entropy situation is one where there are many more. A perfectly stacked deck of cards has low entropy. Any particular shuffled deck has high entropy because there are an enormous number of possible shuffles that all look equally jumbled. The crucial fact is that there are far more high-entropy arrangements than low-entropy ones. If you start in a low-entropy state and let the system evolve under its own dynamics, it is overwhelmingly likely that you will wander into states that can be realized in many more ways. In other words, entropy tends to increase, not because there is a law that says disorder must grow, but because there is a law that says systems will usually move into situations that can be realized in more microstates. The second law of thermodynamics is the formal expression of this tendency. In an isolated system, entropy will not decrease overall. Local fluctuations are possible, but the long-term, large-scale trend is one way. For your coffee cup, that law shows up as cooling. Heat flows from the hotter coffee into the cooler surrounding air until their temperatures are the same. After that, nothing more happens unless you intervene. We are used to seeing this on human scales. What is less intuitive is that the same logic, if applied to the entire cosmos, suggests a cosmic arrow of time. If the universe as a whole can be treated, even approximately, as an isolated system, then its entropy too should be rising. Given enough time, it should approach a state of thermal equilibrium, where no region is significantly hotter or colder than any other, and no more work can be extracted from temperature differences because there are no differences left. This is the seed of the heat death idea, a universe that does not end in a dramatic crash, but in an equilibrium so complete that nothing interesting can happen. Long before we had precise cosmological measurements, some thinkers already sensed this possibility. In the late 18th century, the French astronomer Jean-Sylvain Bailly suggested that cosmic bodies would slowly cool, and that there would come a time when the conditions for life would disappear. He did not have access to the language of thermodynamics as it would later be developed. But the intuition was there. Heat is not infinite. The universe's capacity to maintain warm, active environments is finite. In the 19th century, as steam engines became central to industry and physicists wrestled with the limits of efficiency, these vague worries became sharper. Hermann von Helmholtz and Lord Kelvin, among others, took the newly clarified second law and applied it to everything. If every energy transformation increases entropy, and if the universe is not continually receiving fresh low-entropy energy from outside itself, then it must be slowly running down. It is striking that their picture of cosmic fate grew out of very mundane struggles. How to build better engines. How to understand why some amount of energy always seems to be lost as waste heat. Out of boilers and pistons came a vision of a universe that, in the long run, might cool into a uniform, lifeless state. Modern cosmology adds detail and nuance to that picture, but the core intuition survives. The difference now is that we can look back at the early universe and actually see, in the light of the cosmic microwave background, evidence of how entropy was arranged near the beginning. The cosmic microwave background is a faint glow of radiation that fills space in every direction, a kind of afterglow from a time when the universe was much hotter and denser. Satellites, such as the Planck mission, whose refined results were released in the year 2018, have mapped tiny variations in this glow across the sky. Those variations show that the universe, about 380,000 years after its hot beginning, was astonishingly smooth. The temperature did not vary by more than a few parts in 100,000 from place to place. You might think that a hot, nearly uniform plasma would be a high entropy state. Everything is spread out. There are no stars, no galaxies, no obvious structures. But gravity changes the story. When you include the gravitational field, a smooth distribution of matter actually corresponds to relatively low entropy compared to a clumped distribution. There are far more ways for matter to be arranged in the form of stars, galaxies, and black holes than there are ways to keep it perfectly smeared out. This means that the early universe, despite being hot, was in a remarkably ordered configuration from gravity's point of view. It had a long way to go. Over billions of years, tiny overdensities grew, matter collected into filaments and halos, stars ignited, planets formed, and eventually, somewhere in at least one galaxy, brains emerged that could think about the process. A key conceptual twist lives here. And it is easy to miss because it sounds almost paradoxical. The reason entropy can increase so dramatically over cosmic time is that it started so low. The reason the universe can end in a high entropy stillness is that it began in an unusually special, low entropy state. Sometimes the most astonishing fact is not that things run down, but that they started so wound up in the first place. A simple metaphor can help. Imagine a wind-up music box. When you first twist the key, you are storing energy in an ordered way. The spring inside becomes tense. That tension, that difference between the current state of the spring and its relaxed state, is a kind of low entropy. When you release the mechanism, the music box plays. The gears turn. Sound emerges. Over time, the spring unwinds. The stored energy is dissipated through friction and sound, and the music slows, then stops. The universe, in this metaphor, is like a music box that began already fully wound. The low entropy configuration of the early cosmos is the tension in the spring, the expansion of space, the formation of stars, the chemistry of planets, the emergence of life and mind. All of these are the music, the gears moving as the spring relaxes. When we talk about a possible heat death in the distant future, we are talking about the moment, spread over inconceivable spans of time, when the spring has nearly fully unwound and there is no more stored difference to spend. This metaphor also helps address a common confusion. If entropy is always increasing, how can there be local pockets of order? How can life arise? How can complex structures form? The answer is that the second law applies to the total entropy of an isolated system, not to every region within it. Local decreases in entropy are perfectly allowed, as long as they are more than offset by increases elsewhere. A refrigerator keeps its interior cold, reducing entropy inside, but it does so by dumping waste heat into the room, increasing entropy there by a larger amount. A living cell builds intricate molecules and highly organized structures, but it does so by consuming energy and releasing heat, raising the entropy of its surroundings. In that sense, life is not a violation of the second law, it is one of its most creative expressions. The universe began in a state that left room for enormous increases in entropy. One way the cosmos explores those possibilities is by forming stars and galaxies. Another, more delicate way is by allowing tiny islands of negative entropy flow, such as planets bathed in starlight, where complex chemistry can operate. On at least one such island, those processes gave rise to organisms that wonder about entropy itself. From the standpoint of cosmology, all of that intricate activity is, in a way, a side effect of the universe striving toward higher entropy. The grand trend is from a low entropy, smooth early state to a high entropy, clumpy later state, and eventually, perhaps, to a high entropy, smooth again state, but now smooth in a different way. Matter diluted, black holes evaporated, only faint radiation remaining. If you follow the logic of entropy forward using our current best physics, you are led to a picture of a universe in which free energy gradients disappear. No hot stars shining into cold space, no rotating black holes bleeding energy into their environment, no temperature differences to drive engines, weather systems, or metabolism. Particles and photons may still exist, but they will be distributed in such a way that no large-scale, low-entropy structures can form. The arrow of time, as we experience it, becomes hard to define when there are no longer processes that can distinguish a before and an after. That is one of the main answers that physics offers to the question, how does it end? Not with a bang that instantly erases everything, but with a long, slow loss of usable difference. There is a quiet irony here. The same law that points toward eventual stillness is also the law that made motion, change, and complexity possible in the first place. Without a low entropy beginning, there would be no directionality for time to have. Without an abundance of ways to increase entropy, there would be no reason for stars to form, no pressure for matter to clump, no space for chemistry and biology to unfold. When we look at the universe today and see layered galaxies, bright nebulae, and living worlds, we are seeing the consequences of entropy on the way up. When we imagine the far future and talk about heat death, we are imagining entropy approaching its ceiling. The middle and the end are written by the same rule. It can be tempting to treat that rule as an enemy, as if entropy were a kind of cosmic vandal erasing all that is interesting. But from another angle, it is the author of every story that ever happens. The universe began with a wound-up spring. The music it plays while unwinding includes everything from the first stars to your cup of cooling coffee. If there is a time when the music finally fades into a soft, featureless hum, that time is not separate from the beauty that came before. It is the other side of the same process. By the time you start to wonder how the story ends, it is easy to forget that you are living inside one of its brightest chapters. Right now, in this cosmic moment, the universe is in what astronomers sometimes call the Stelliferous Era, the age of stars. If you go outside on a clear night and look up, it does not feel like a rare or fleeting condition. The sky is crowded with points of light. Even in a city, where most of them are drowned by artificial glare, the idea that space is full of suns feels like a simple, permanent fact. But it is not permanent. It is a phase. Our own sun is one example among hundreds of billions in our galaxy, and more broadly among uncountably many scattered across the observable universe. It has been shining for about 4.5 billion years, quietly fusing hydrogen into helium in its core. It will continue to do so, in a broadly similar way, for roughly another 5 billion years. Those numbers are already large by human standards, big enough to feel like forever. Civilizations can rise and fall many times over in a single narrow slice of that timeline. Yet for the sun itself, this is only one act in a longer play. Once it has used up the hydrogen in its core, it will change. The outer layers will swell. It will become a red giant, engulfing the inner solar system in a slow, luminous crisis. Later, it will shed those outer layers into space, leaving behind a hot, dense core, a white dwarf roughly the size of Earth, packed with the mass of a star, cooling over trillions of years. That path, from main sequence star to red giant to white dwarf, is the gentle version of stellar death. More massive stars live more violently. To feel that violence, it helps to remember a particular night in human history. In late February of 1987, observers in the southern hemisphere noticed a new star in the sky, visible to the naked eye where nothing bright had been before. It appeared in the direction of the Large Magellanic Cloud, a small companion galaxy to our Milky Way. What they were seeing was supernova 1987A, the explosion of a massive star that had reached the end of its fuel-burning life. For a few weeks, that single event outshone the entire galaxy that contained it. Neutrinos, nearly massless particles produced in the collapsing core, streamed through space and through the Earth. What had been a stable, luminous star suddenly became a shockwave, a spray of heavy elements, and, at the center, a dense remnant, a neutron star. Or perhaps, depending on details of mass and collapse, a black hole. This is the other main path of stellar death. Small and medium stars, like the Sun, end as white dwarfs, slowly fading. Larger stars die as supernovae, collapsing and rebounding in titanic blasts that forge many of the elements in our bodies and scatter them into space. Their cores, crushed by gravity, become neutron stars, city-sized spheres of nuclear matter, or cross the threshold into black holes, regions where gravity is so intense that not even light can escape. If you imagine the universe far into the future, it is these remnants that will dominate the landscape. But before we go there, it is worth lingering on the present era with a slightly different question. How long does this age of starlight last? Star formation is not a constant, unchanging process. Observations of distant galaxies whose light left them billions of years ago show that the universe was more vigorously forming stars in the past than it is now. There was a time, a few billion years after the hot beginning, when galaxies were thick with cold gas and the rate of new star birth peaked. Since then, that rate has been declining. Gas is used up, heated, blown out by stellar winds and supernovae, or locked into long-lived stars that will not explode. Our own era is already on the downward slope of that curve. New stars are still forming in the Milky Way, in glowing regions like the Orion Nebula, but not as frantically as in the cosmic youth. Give the universe enough time, and this decline continues. Calculations in modern astrophysics suggest that over timescales of around 10 to the 13th to 10 to the 14th power years, 10 trillion to 100 trillion years, almost impossibly far beyond the current age, almost all stars that can ever shine will have done so. The vast gas reservoirs that fuel star formation will be exhausted or dispersed. No fresh, bright, hydrogen-burning stars will be born. The ones that exist will either have evolved into white dwarfs, neutron stars, or black holes, or in the case of the least massive red dwarfs, will be approaching the end of their astonishingly long lives. From the perspective of a hypothetical observer living in that future, the night sky would be unrecognizable. Where we see a thick band of Milky Way starlight, they might see only a sparse archipelago of red embers. Over further eons, even those would wink out, one by one. The age of stars, which feels to us like the default condition of the universe, would be revealed as a brief flare in a much longer darkness. There is something quietly unsettling in that realization. Many of our stories about apocalypse are, by comparison, claustrophobically local and fast. In a film like Interstellar, released in the year 2014, the crisis is planetary and near. Dust storms ravage fields. Crops fail. Earth becomes less and less habitable over the span of a few generations. The urgency is immediate. You can imagine parents and children arguing over whether to stay or to leave. Cosmology, on the other hand, is working with a different kind of ending. The slow shuttering of star formation, the eventual death of existing stars, and the conversion of luminous matter into faint remnants and dark holes. All of this unfolds over times that dwarf the age of our species, our planet, even our galaxy. It is an apocalypse stretched thin, not over years or centuries, but over towers of magnitudes of years, stacked one upon another. It is so gradual that no single generation in that future would feel the sky change drastically. Only when you compress the timeline in your mind does it become visible as a fall. It is helpful to remember what is really ending in this first stage. Stars are not just pretty lights, they are engines. A star takes nuclear fuel in most cases, hydrogen, and crosses an entropic gradient. Binding light nuclei into heavier ones releases energy, because the final configuration is lower in energy than the initial one. That energy escapes as light and heat, and in doing so, it can power other processes, warming planets, driving winds, supporting chemistry. For any civilization, at least with physics as we currently understand it, access to that kind of free energy is a precondition for long-term survival. You can, in principle, build enormous structures to capture more of a star's output. You can stretch your budget by moving to cooler stars that live longer, or by using matter more efficiently. There are speculative ideas about advanced civilizations that surround their stars with swarms of collectors, or that migrate from one star system to another as local conditions change. But what you cannot do is outrun the cosmic fact that nuclear fuel is finite. Once hydrogen is fused into heavier elements, it is not easily turned back. The very reactions that keep a star shining also carry it toward its exhaustion. This is why the twilight of the Stelliferous Era marks a practical boundary, regardless of more exotic possibilities like vacuum decay or Big Rip scenarios. Even if the underlying fabric of space-time remains stable for unimaginable stretches of time, even if no sudden, catastrophic phase change arrives, the slow shutdown of fusion sets an outer limit on how long anything resembling life as we know it can operate freely. It is possible to imagine ways of eking out existence in a universe of remnants. White dwarfs, for instance, can stay warm for trillions of years as they slowly cool. A civilization might find ways to tap that glow. Neutron stars have magnetic fields and rotational energy that could be harvested. Black holes, as we will see later, radiate faintly through quantum effects and might be used as extremely long-lived energy sources by truly patient beings. These ideas belong more to the borderland between physics and speculative engineering than to observation. But they are not pure fantasy. They reflect the creativity of people who have taken the long-term evolution of stars seriously and asked what options remain once the easy energy of a main sequence star is gone. Still, those options are limited. As time passes, the universe's energy sources become weaker, more diffuse, and harder to reach. The costs of survival, measured in effort per unit of usable energy, rise. There may come a point, even before any strict heat death, when the practical challenge of staying active overwhelms any finite strategy. The universe, in that sense, becomes hostile not through any intent, but through sheer, patient attrition. This picture stands in stark contrast to how most cultures have imagined the end of days. The word apocalypse, in its original sense, means unveiling or revelation. In many religious traditions, it is an event, sudden, decisive, morally charged. The world as we know it is overturned, replaced by a final judgment, a new creation, or an eternal stasis of a different kind. Time, in those narratives, is relatively short. The horizon is never more than a handful of generations away, sometimes much less. Physics offers, instead, a slow apocalypse. No trumpets. No single day when everything changes for everyone at once. Just stars aging, one by one, across a canvas that grows colder and emptier. The revelation, if there is one, lies not in a miraculous interruption of natural law, but in the realization that natural law itself, extrapolated faithfully, has teeth. There is a strange comfort in the slowness. For us, as the particular fragile species watching from one small planet, the demise of starlight is so far away that it almost does not register as a threat. We can allow ourselves the luxury of thinking about it as a concept, rather than as a fate. But for the universe considered as a whole, it matters. It is the first clear, empirically grounded chapter in the story of how things run down. We do not need to invoke unknown physics to see this. We do not need to guess at the behavior of dark energy on scales of 10 to the power of 100 years. The life cycles of stars are already written in the fusion reactions we can study in laboratories and in the stellar populations we observe in different galaxies at different ages. The decline of star formation is written in deep surveys of the sky, in the statistics of galaxies that look younger and older at different distances. The eventual exhaustion of nuclear fuel is not a speculative quirk. It is the straightforward consequence of finite resources in a finite, though vast, system. If you zoom out, the Stelliferous Era becomes a bright band in the timeline of the universe. Before it, in the very early ages, the cosmos was simpler. Mostly hot radiation, simple nuclei, and gradually assembling clouds of gas. After it, if our understanding is roughly right, the cosmos is darker, populated by the dead and cooling remnants of those same stars, and by black holes that will, for a long time, be the dominant, large-scale structures. Even before we grapple with the more exotic possibilities that physicists have explored, vacuum decay, Big Rip, cyclic bounces, this basic arc gives us a first answer to the question of how the universe ends. The first ending is not of space-time itself. It is the end of the bright era, the closing of the window in which new stars can form freely and burn steadily, the slow fading of the lights. Standing under the night sky now, it is hard to feel that you are living in that window, because for us, it spans all of history and all conceivable future. But in the language of cosmic time, this is a middle chapter with a beginning and an end. Once the last new stars are born and the last existing stars go out, the universe will have crossed an important threshold. It will still exist. It will still have matter and radiation and laws. But the most familiar beacons of cosmic life will be gone. That twilight, that gradual dimming of starlight, is the first ending we can see clearly when we let physics run its course. When the last ordinary stars step down from the stage, the universe does not fall silent. It changes register, from the bright voices of fusion to the low, persistent murmur of what is left behind. Astronomers sometimes call this next act the degenerate era. Fusion, the process that made stars shine, has mostly ended, but matter does not simply dissolve. It clings together in strange, compact forms that obey quantum rules as much as classical ones. The result is a cosmos populated less by blazing suns and more by the dense leftovers of their lives: white dwarfs, neutron stars, and black holes. To feel what this means, it helps to stand close, at least in imagination, to a single white dwarf. Take a star like our Sun and follow it forward through its life. After hundreds of millions of years as a red giant and the shedding of its outer layers into space, what remains is the core, roughly the mass of the Sun, squeezed into a sphere only a little larger than Earth. That is a white dwarf. There is no fusion in its core anymore. It shines only because it is still hot, cooling slowly, radiating away the heat left over from its formation. The material inside is extreme. Atoms are crushed so close that their electrons form a kind of quantum sea. The pressure that holds the star up is not thermal pressure from hot gas, but degeneracy pressure from those electrons, a manifestation of the fact that certain particles cannot share the same quantum state. The densities are so high that early estimates, when objects like Sirius B were first studied in the 19th century, startled astronomers. Here was a companion to a familiar bright star, tiny and yet so massive that its matter seemed almost unthinkable. A white dwarf does not live fast and die young. It cools slowly, over trillions of years, fading from white to red to infrared to black, becoming what theorists call a black dwarf. An object no longer emitting significant light, still holding its mass together in a silent, crystalline structure. In the long twilight after the age of stars, white dwarfs and their darker descendants will be among the main reservoirs of ordinary matter. Neutron stars, by contrast, come from more violent endings and live even closer to the edge of what matter can endure. When a massive star collapses and blasts off its outer layers as a supernova, its core can be crushed to densities comparable to the nucleus of an atom. Protons and electrons merge into neutrons. The result is a sphere only about the size of a city, with the mass of the Sun or more, held up not by electron degeneracy, but by neutron degeneracy and nuclear forces. In the late 1960s, an unexpected signal revealed just how strange these objects could be. In the year 1967, a graduate student named Jocelyn Bell Burnell noticed regular, pulsing radio signals in data from a new radio telescope. The pulses were astonishingly precise, repeating with a stability that led the team, half-jokingly, to label the first source as coming from possible little green men. But the explanation was even more interesting. They had discovered pulsars, rapidly spinning neutron stars, whose intense magnetic fields beam radiation into space like lighthouse beams. Each pulse marks a rotation, some occurring many times each second. The existence of pulsars showed that the corpses of stars could be spectacular. They also made it clear that in the future graveyard universe, many of the most active remaining objects would be dead stars repurposed into cosmic clocks and particle accelerators. Over truly long stretches of time, even these compact remnants are not static. White dwarfs continue to cool. Quantum processes, such as tunneling, may allow particles within them to rearrange in ways that slowly transform their interiors. Two white dwarfs in a close binary system can spiral together and merge, briefly reigniting nuclear reactions in a thermonuclear supernova. Neutron stars can collide, releasing bursts of gamma rays and forging heavy elements like gold and platinum in the resulting kilonovae. Even in a universe where ordinary star formation has ceased, rare interactions between remnants can produce brief flashes of renewed energy. But as the universe expands and time goes on, these interactions become rarer. Objects drift farther apart. Orbits widen or are perturbed by gravitational encounters. The graveyard becomes more sparse. Into this landscape step black holes, the final predators of structure. A black hole begins as a collapsed star or as the outcome of an even more massive gravitational collapse in the centers of galaxies. It is described in the simplest terms by its mass, its spin, and its charge. Surrounding it is an event horizon, a one-way surface beyond which light and matter cannot return to the outside universe. Anything that crosses that horizon becomes part of the hole's hidden interior, adding to its mass and slightly expanding the horizon's size. In the current universe, black holes already play a major role. Many galaxies, including our own, harbor supermassive black holes at their centers, with masses of millions or billions of suns. Gas and stars falling into these central engines can release enormous amounts of energy in the process, lighting up as quasars and active galactic nuclei. In the far future, when ordinary star formation ends and galaxies have had time to interact and merge, black holes are expected to grow even more dominant. Galaxies do not stay neatly separate forever. Over billions of years, their mutual gravity pulls them together. Collisions and mergers rearrange their contents into larger, more massive conglomerates. Each merger brings the central black holes closer to one another until they eventually spiral inward and combine. You can think of this as a slow concentration of mass into fewer, heavier objects. Where there were once many small galaxies with modest black holes, there may ultimately be a single large structure with a central black hole of astonishing mass, quietly feeding on whatever gas, stars, and remnants are sent its way. On April 10, 2019, the Event Horizon Telescope collaboration released the first image of the shadow of a black hole in the center of the galaxy known as Messier 87. The orange ring and the dark circle within it, a silhouette against a glowing disk of gas, gave humans a direct, visual confirmation of an object we had previously known, mostly through indirect effects. The image itself shows the region just outside the event horizon, not the interior. Yet it brought into focus, quite literally, the kind of entity that theory suggests will be one of the primary actors in the universe's later chapters. As ordinary stars fade and compact remnants drift, black holes continue their work. They swallow stray white dwarfs, unlucky neutron stars, and loose gas. They merge with each other when their host galaxies collide. In doing so, they emit gravitational waves, ripples in space-time itself that carry energy away. Over time, the population of black holes changes. Fewer in number, greater in mass. This period is sometimes imagined as a merger era, though in practice, it is more of a long tail of interactions than a sharply defined epoch. Once galaxies have mostly merged into large clusters or single giant galaxies, and once the available supply of matter to feed black holes dwindles, the frequency of dramatic events drops. But for a long time, cosmically speaking, black holes will be the main crucibles where gravity still does something visibly dynamic on large scales. According to current models, this graveyard phase, dominated first by white dwarfs and neutron stars, and increasingly by black holes, could last for an absurdly long time. We are talking about durations that make even the trillions of years associated with white dwarf cooling seem modest. During these spans, the universe continues to expand. The background radiation cools further. Gravitationally bound structures, like galaxy clusters, remain held together. But the space between those structures stretches so much that they slip forever beyond one another's horizons, unable to exchange light. Within each bound region, the compact remnants orbit and interact in ever more diffuse halos. Occasionally, two objects will come close. A white dwarf might plunge into a black hole, spiraling in and emitting a final burst of energy in its death. A neutron star may be captured and torn apart, but most remnants will simply circle quietly, their orbits shaped by long-past encounters. It is in these imagined futures that science fiction often begins to improvise. Authors and game designers imagine civilizations so advanced that they have learned to survive in this graveyard universe by tapping into the remaining energy sources. They might mine the surfaces of white dwarfs, capturing the faint but steady trickle of heat. They might orbit just outside the event horizon of black holes, using the extreme gravitational environment to extract energy from infalling matter or from the hole's rotation. They might build structures that span light years, coordinating their activities across vast, dimly lit spaces. Many of these visions are wildly beyond any technology we can realistically foresee, but some of the underlying ideas are rooted in real physics. For example, it is in principle possible to extract energy from a rotating black hole through processes similar to the Penrose mechanism, in which particles gain energy at the expense of the hole's spin. The notion of using compact objects as long-term power sources arises naturally when you realize how slowly some of them release their stored energy. Whether any civilization could persist long enough to exploit these strategies, and whether it could do so without being ground down by the increasing thinness of usable energy, is another question. But as thought experiments, they highlight a simple point. Even in a universe dominated by stellar corpses, there remain gradients, however faint, that could be harnessed. Still, the trend is clear. The overall inventory of free energy declines. The bright, chaotic era of star formation and youthful galaxies gives way to a sparser, more austere landscape. The rate of dramatic events slows. The cosmos, on large scales, looks more like a graveyard than a nursery. If you could somehow freeze the universe at one of these late stages and take a snapshot, you would see a dark archipelago of remnants. Here and there, a fading white dwarf, a few neutron stars, spinning more slowly now, their pulsar beams weakened or gone, dominating the centers of bound regions, enormous black holes, perhaps ringed by thin, cold disks of whatever material remains available to fall in. Beyond these islands, space stretched so far that other clusters of remnants are permanently out of causal contact, their light redshifted into undetectable wavelengths. The bright, familiar universe, the one of star fields and spiral galaxies, of the Milky Way as a river of light across the sky, is gone. What remains is quieter, colder, and stranger. And yet, even here, the story is not finished. Because black holes, for all their reputation as final, unchanging endpoints, are not truly forever either. There is an even slower process at work, one that will eventually turn even these darkest objects into fading whispers of radiation. The graveyard universe is not the last chapter, only the setting in which the next, almost unimaginably patient, transformation begins. By the time the universe has become a cemetery of remnants, black holes look like the last things that could ever change. For a long time, that is exactly how we thought of them. In the popular picture, a black hole is the ultimate one-way trap. Light goes in and never comes back out. Matter falls in and is never seen again. Whatever crosses the event horizon is cut off from the rest of the universe, locked behind a boundary from which no signal can escape. In that view, black holes are not just endpoints for stars. They are endpoints for processes themselves. Then, in the 1970s, something quietly subversive happened. Stephen Hawking, working at the intersection of general relativity and quantum field theory, began asking what happens when you put a black hole into a universe where the quantum vacuum is never completely empty. Even in what we call empty space, quantum fields fluctuate. Pairs of particles and antiparticles flicker into existence for brief moments and then annihilate again. That restless background is usually invisible to us. But near the event horizon of a black hole, it changes the story. In a paper with the deceptively understated title Black Hole Explosions, published in the journal Nature on March 1st, 1974, Hawking showed that when you take those quantum fluctuations seriously, black holes should not be perfectly black. They should emit a faint thermal radiation, now called Hawking radiation. And if they are radiating energy away, they should also be losing mass. Given enough time, they should evaporate. For many physicists, this result was shocking. Black holes had been understood, up to that point, as objects from which nothing can escape. The idea that they could slowly leak energy and eventually disappear seemed almost like a contradiction in terms, yet the math, built from well-tested theories, pointed in that direction. The intuitive picture often offered goes like this. Near the event horizon, a particle-antiparticle pair pops into existence out of the quantum vacuum. Normally, such pairs meet again and annihilate almost immediately, returning their borrowed energy to the vacuum. But if this happens right on the edge of a black hole, there is a small chance that one of the pair will fall past the horizon while the other escapes to infinity. From the point of view of the outside universe, it is as if the black hole has emitted a particle. Conservation of energy demands that the energy of this escaping particle must come from somewhere. It comes, effectively, from the mass energy of the black hole itself. Over many such events, the black hole loses mass, and its horizon shrinks. It is important to say that this is not a literal story about little particles jumping off the surface like sparks. The real calculation is more abstract, involving how quantum fields behave in curved space-time. But the image of pairs near the horizon, one falling in and one escaping, gives a useful handle on something that is otherwise deeply counterintuitive. The crucial point is that the temperature associated with this Hawking radiation is inversely related to the mass of the black hole. The more massive the hole, the colder its radiation. A small black hole radiates more strongly and evaporates quickly. A huge one radiates extremely feebly and evaporates astonishingly slowly. The timescales involved are part of what makes this story feel almost unreal. A black hole with a mass comparable to that of the Sun would take around 10 raised to the power of 67 years to evaporate completely. That is a 1 followed by 67 zeros in years. A supermassive black hole, like the monsters that sit at the centers of galaxies, with masses in the range of millions or billions of suns, would take around 10 raised to the power of 106 years or more to disappear. By comparison, the current age of the observable universe is on the order of 10 billion years. That number, already dizzying when you first hear it, becomes almost trivial next to the evaporation times. If you compress the entire life of the universe so far into a single second of a film, the full evaporation of a large black hole would stretch longer than any feature-length movie you have ever imagined. Longer than the history of film itself, by an absurd factor. These are timescales that make even stars look like mayflies. In popular culture, black holes are usually presented in a very different way. Think about the depiction of Gargantua, the black hole in the film Interstellar, released in the year 2014. Designed with input from physicist Kip Thorne, Gargantua appears as a luminous, distorted ring of light, lensed around a dark center. A swirling accretion disk feeding the central hole. Time dilation effects near its horizon become important for the characters. The environment is dramatic, visually and physically intense. Hawking radiation, by contrast, is almost the opposite of that cinematic grandeur. For astrophysical black holes formed from stars or galactic centers, the Hawking temperature is far colder than the current temperature of the cosmic microwave background. They absorb more radiation from their surroundings than they emit. Only when the universe itself has expanded and cooled, so much that the background temperature has dropped below the black hole's Hawking temperature, will the net flow reverse, and evaporation truly begin. Even then, for large holes, the radiation is feeble, almost ghostly. No bright ring, no roaring disk, just a slow seep of energy into space. There is a subtle, almost philosophical tension built into this story. If a black hole evaporates away completely, what happens to the information about everything that fell in? In classical general relativity, the answer would be simple. It goes inside and stays there. The event horizon hides the details from the outside world, but in principle, the information could be thought of as still existing within the region from which nothing can return. Hawking's semi-classical calculation, though, seems to suggest that the radiation coming out is thermal, carrying no detailed imprint of what went in. If the black hole eventually disappears and the radiation is purely random, then the initial information appears to be lost. This is called the black hole information paradox, and it has driven decades of work in theoretical physics. On one side, the principles of quantum mechanics are built on the idea that information is never truly destroyed, only scrambled. On the other side, the naive interpretation of Hawking radiation seems to violate that principle. Reconciling the two has led to ideas about holography, where the information about the interior is somehow encoded on the horizon surface, about subtle correlations in the radiation that might preserve information after all, and about the need for a full theory of quantum gravity that goes beyond our current tools. For our purposes, we do not need to take a stand on which resolution is correct. What matters is that black holes, once thought, if not immortal, then at least indefinitely persistent, are now seen as transients in an even longer game. They have a reign, but they also have a slow death. Imagine the universe far enough in the future that the age of star formation is long past. White dwarfs and neutron stars have cooled or collided. Most matter that was susceptible to being swallowed by black holes has already fallen in. There is no fresh gas to feed luminous accretion disks. In each gravitationally bound region, a handful of massive black holes sit in quiet dominance, like heavy stones at the bottom of a drained riverbed. At this point, the background radiation temperature of the universe has dropped below the Hawking temperature of those holes. They no longer gain energy from the environment. They lose it. The process is still extraordinarily slow, but over timescales far exceeding anything we have considered so far. The black holes begin to shrink. As they lose mass, their temperature rises. They radiate more strongly. A feedback loop develops. Smaller means hotter. Hotter means more intense radiation, faster loss, and further shrinkage. For most of their life, black holes evaporate at a glacial pace, almost imperceptibly. But near the end stages, the process accelerates. The final phase, in which a small black hole converts its remaining mass into a burst of high-energy photons and other particles, is much more dramatic, though it happens in a universe that has few, if any, observers left to notice. There is an interesting twist here. Some models of the very early universe allow for the formation of so-called primordial black holes. Tiny black holes born not from stars, but from density fluctuations in the first fractions of a second after the hot beginning. Depending on their initial mass, such black holes could have evaporated already, or could be evaporating now. Very small ones would disappear quickly. Ones with masses similar to mountains or asteroids would last longer. Some speculative ideas suggest that evaporating primordial black holes could contribute to observable phenomena today, such as certain gamma-ray signals. So far, however, there is no convincing evidence for their existence. Observations constrain how abundant they could be. Instruments searching for their supposed evaporation bursts have not found clear signatures. In that sense, primordial black holes act as a bridge between end-of-universe physics and present-day astronomy. A reminder that our most distant extrapolations sometimes loop back into testable questions here and now. Whether or not primordial black holes are real, the general principle remains. Black holes radiate, they lose mass, they die, at least as black holes. When the last of them has evaporated, what is left of the matter content of the universe will be extremely sparse. Some particles created during the final bursts may collide or interact. But in a universe that is already vast and dilute, most will simply stream outward forever, redshifting to longer and longer wavelengths as space continues to expand. From a human vantage point, it is tempting to think of the reign of black holes as an almost eternal era. The timescales are so large that they make everything else look brief. Yet, on the scale of the full cosmic story, they are still temporary characters. The same logic that turned the bright, flamboyant lives of stars into quiet, cooling remnants also turns the apparently absolute darkness of black holes into a phase that can be outlived. There is a kind of existential echo in this. We are used to thinking of black holes as the ultimate erasers, swallowing the details of whatever falls in, leaving only mass and spin behind. The discovery of Hawking radiation complicates that, but it also does something subtler. It shows that even the universe's best approximations of permanence are, at bottom, conditional. Given enough time and the right perspective, they, too, are processes. When you follow this all the way through, you arrive at a picture that is both simple and hard to look at directly. Once the last black hole evaporates, the universe enters a phase where almost all structure is gone. No stars, no galaxies, no dense remnants. The grand architecture of cosmic history has been flattened into a thin, cold sea of particles and low-energy radiation, stretched over an expanding space-time. It is in that nearly featureless aftermath that the idea of heat death becomes more than a phrase. The universe has not disappeared, but almost everything that once made it a place of vivid change and complexity has been erased. What remains, and what it means to speak of time in such a setting, is the next step in understanding how a universe can end without truly stopping. Once almost all structure has faded, and even black holes are slowly leaking themselves away into the dark, you might think the universe's fate is sealed beyond question. But there is a quieter, more pervasive actor that has been steering everything for billions of years already. And our picture of the end depends almost entirely on what it truly is. We give it a simple name: dark energy. It first stepped into the story through those distant Type 1, a supernovae observed in the late 1990s, when two independent teams found that faraway exploding stars were dimmer than expected. On a cold day, in January of 1998, the announcements began to ripple through the community. The expansion of the universe was not slowing down under gravity's pull. It was accelerating. To make sense of this, cosmologists did something almost embarrassingly straightforward. They took the equations of general relativity, moved a term from one side to the other, and declared that empty space itself seems to carry a kind of energy that pushes things apart. When you add up the best measurements we have today, this dark energy appears to make up around 70% of the total energy content of the observable universe. Dark matter, which pulls things together, contributes most of the rest. Ordinary matter, the atoms in stars, planets, and you accounts for only a small remainder. Yet despite its dominance, dark energy is not something we can put in a bottle or detect in the lab. We infer it from its effect on the cosmic expansion. The simplest way to model dark energy is to assume that it is a cosmological constant, a fixed energy density associated with empty space itself. That idea actually predates the supernova discoveries. It is essentially the same term Einstein introduced to keep the universe static, reinterpreted as a driver of acceleration instead of a brake. In this picture, every cubic meter of space has the same tiny amount of vacuum energy, all the time, everywhere. If that is really the whole story, the future unfolds in a particular way. As the universe expands, there is more space, and therefore more total vacuum energy. But the density stays constant. Gravity from matter and radiation grows less important as they dilute. The expansion rate approaches a steady, accelerated behavior determined mainly by the cosmological constant. Galaxies not gravitationally bound to us recede faster and faster, eventually crossing our cosmic horizon and disappearing from view forever. The local pockets that remain bound, our galaxy and its close neighbors, merged into one structure, continue their internal evolution. But the larger universe becomes increasingly fragmented. In that scenario, the big freeze, or heat death, we have been circling around is the likely endgame. Star formation winds down, existing stars exhaust their fuel. White dwarfs cool, neutron stars spin down. Black holes, slowly and almost invisibly, evaporate via Hawking radiation. What is left is a thin soup of low-energy photons, neutrinos, and a few other stable particles, spread sparsely through an ever-expanding space. The cosmological constant keeps doing what it does, stretching the stage, even as the play has effectively ended. But the cosmological constant is only the simplest guess, not a proven fact. Dark energy could be more exotic. In many models, physicists describe its behavior with an equation of state parameter, usually called W, which relates its pressure to its energy density. For an exact cosmological constant, W is equal to -1. Observations so far suggest that W is very close to this value, perhaps exactly equal, but the uncertainties leave room for other possibilities. One of the most unsettling of those possibilities is something called phantom energy, where W is less than -1. In that case, the energy density of dark energy does not stay constant as the universe expands. It grows. Space is filled with a form of energy that becomes more and more dominant, driving the expansion faster and faster in a runaway process. In 2003, physicist Robert Caldwell and colleagues explored this idea in a paper with a deliberately dramatic title, Phantom Energy and Cosmic Doomsday. They asked a simple question: if dark energy behaves like this, what happens not just to the expansion rate, but to everything? The answer, in their models, is the Big Rip. The story unfolds in stages. At first, the universe behaves much as in the cosmological constant case. Acceleration, structures receding, but as phantom energy strengthens, the repulsive effect of dark energy overcomes gravity on larger and larger scales. Far in the future, galaxy clusters, which are currently held together against expansion by their mutual gravity, would be pulled apart. Later, individual galaxies would be torn. Stars would drift away from one another as the bonds of gravity that hold them in orbit are overwhelmed. Closer to the final moment, the scale of destruction shrinks. The Milky Way, or whatever merged structure replaces it, would be unbound tens of millions of years before the end. Solar systems would be disrupted even later. Planets would be wrenched from their stars, moons from their planets. Eventually, the tidal forces from the accelerating expansion would become strong enough to tear apart planets themselves, then molecules, then atoms. In the last tiny fraction of the universe's lifetime, even atomic nuclei could be ripped apart as the scale factor of the universe races toward infinity in a finite time. It is a cinematic vision, a universe that does not simply cool and fade, but is literally shredded by its own expansion. Some people find the Big Rip morbidly fascinating, because it offers a kind of cosmic horror different from the slow melancholy of heat death. Others find it simply too speculative to take seriously. From the standpoint of current data, phantom energy is not favored. Observations from the Planck satellite's maps of the cosmic microwave background, combined with supernova surveys and measurements of how galaxies cluster on large scales, are all consistent with W being very close to -1. But the error bars are not zero. They leave room, however small, for W to be slightly above or slightly below that value. In other words, we cannot yet say with absolute confidence whether the universe is ruled by a true cosmological constant or by something that only imitates one for a while. On the other side of the emotional spectrum lies the Big Crunch, the older favorite before cosmic acceleration was discovered. In a crunch scenario, the expansion of the universe eventually slows, halts, and reverses. Galaxies that are now moving away from each other would, in the far future, begin to fall back. The universe's scale factor would shrink. Densities and temperatures would rise. In the limit, everything would collapse into a state as hot and dense as, or perhaps even more extreme than, the early universe's beginning. There is a certain narrative satisfaction in the Big Crunch. The cosmos begins in a bang and ends in a reverse bang. Time, in some speculative versions, might even loop, with the end and the beginning indistinguishable in some deep sense. Philosophically and visually, it has appealed to many thinkers and writers. For decades, it was a serious contender in cosmology classes. Will gravity win and pull everything back? Or will expansion win and leave a drifting, cooling universe? The discovery of accelerated expansion in the late 1990s shifted the balance. If dark energy is a cosmological constant or behaves similarly, then the break that would be needed for a crunch simply is not there. The universe does not seem to be on a path toward recollapse. Instead, it looks like a system in which expansion will continue indefinitely. There is, however, a loophole. Dark energy might not be constant. It could change sign, or decay into other forms of energy, or somehow shut off in the far future. In some models, this could allow the current acceleration to be a temporary phase, after which gravity from matter and radiation could reassert control and bring about a recollapse. These models are more elaborate and less supported by data than the simple cosmological constant, but they exist in the space of possibilities. When you step back and look at these three broad fates, heat death under a cosmological constant, big rip under phantom energy, and big crunch under a changing dark energy, the emotional palette is surprisingly varied. Heat death is a fade-out. It is the cosmic equivalent of a film that runs until the last frame, which is not black but almost featureless. The credits never roll, but nothing new appears on screen. For some, this is strangely soothing. The universe does not end in fire, but in silence. There is no single catastrophe to fear. Everything simply winds down. The big rip is a horror cut. The universe remains full of structure until close to the end, and then, as the acceleration runs away, everything is torn apart step by step. It is apocalyptic in a more familiar sense, though played out on cosmological scaffolding. A clear timeline, a recognized doomsday, an unambiguous final second. The big crunch is a return. The universe begins hot and dense, cools and expands, forms stars and galaxies, and then, at some point, turns around and rushes back into heat and density. It is like watching a film of the Big Bang played in reverse. Some people find comfort in the idea that everything comes back together. Others find it claustrophobic. Documentaries and long videos about cosmology often lean into whichever of these moods matches their tone. A calm, late-night exploration might focus on heat death, emphasizing the absurd timescales and the quietness of the end, inviting viewers to feel small but oddly peaceful. A darker, more dramatic piece might dwell on the big rip, with animations of galaxies being pulled apart and atoms stretched beyond recognition. A nostalgic or philosophically inclined story might resurrect the big crunch as a way to talk about cycles and returns, even if it notes that current data does not favor that outcome. Underneath the different atmospheres, however, there is a shared dependency. All of these fates depend crucially on dark energy's true nature. Is it a simple cosmological constant? Is it a field that changes over time? Does it interact with matter in subtle ways we have not yet seen? Or is the entire framework we are using to describe it missing something essential? One hint that our understanding is incomplete comes from what cosmologists call the Hubble tension. Measurements of the universe's expansion rate made from nearby objects such as Cepheid variable stars and supernovae in relatively close galaxies consistently give a value that is higher than the value inferred from the early universe, as encoded in the pattern of fluctuations in the cosmic microwave background measured by Planck in 2018. The discrepancy is small in absolute terms, but stubborn, surviving multiple attempts to explain it away through measurement errors or underestimated uncertainties. Some researchers think the Hubble tension might be pointing toward new physics, perhaps a subtle modification in how dark energy behaves over time, or a change in the composition of the universe between the early and late epochs. Others suspect that unrecognized complexities in the data analysis are to blame. Either way, it is a reminder that our grip on cosmic acceleration is less firm than the clean plots of textbooks would suggest. So where does that leave us? If the question is simply, how will it end? The most honest answer today is that our best data support a universe heading towards something like a heat death under continued accelerated expansion. Dark energy behaves, so far as we can tell, very much like a cosmological constant. The models that fit supernovae, cosmic microwave background maps, and galaxy surveys all together tend to converge on a future in which expansion continues, structures thin out, and, over inconceivable times, stars, remnants, and black holes fade into a cold, dilute bath of radiation. But this answer carries an asterisk. It assumes that the behavior of dark energy we infer over a modest range of cosmic history really does extend indefinitely into the future. It assumes that the slight tensions in the data do not grow into cracks that demand a new framework. It assumes that our extrapolation of general relativity and quantum field theory, tested in laboratories and within a small patch of space-time, remains trustworthy over spans that dwarf the age of our species by factors we can barely write down. A single generation ago, dark energy did not appear in cosmology textbooks at all. Before the late 1990s, many diagrams of the universe's fate showed only decelerating expansion and possible recollapse. Then, a handful of faint, distant supernovae forced a change of mind. It is entirely possible that future observations of even more distant supernovae, of gravitational waves from the far universe, of subtle imprints in large-scale structure we have not yet mapped, will revise the script again. For now, though, if we imagine the universe's most probable future, we are imagining a cosmos whose end is written in the behavior of a component we barely understand, discovered within the lifetimes of many people still alive. The fate of everything may depend on a quiet pressure in empty space, a term in our equations that could yet turn out to be a placeholder for something stranger. If the slow fade of heat death feels like a story that simply runs out of pages, there is another kind of ending that lurks in the equations, one that feels less like a fade and more like a trapdoor. So far, we have imagined the universe drifting towards stillness under rules that stay the same. The laws of physics, in that picture, are fixed. The constants remain constant. Dark energy keeps doing whatever it is doing now. Entropy climbs. Structures fall apart or evaporate. Nothing dramatic happens to the underlying machinery. But quantum field theory, our best description of matter and forces at small scales, quietly entertains a more sudden possibility. The universe might not just run down, it might jump. The idea goes under the name of false vacuum decay. The phrase sounds technical, but the core image is almost childlike. A ball on a hillside that thinks it has reached the bottom. Imagine a smooth slope with a little dip in it, and then farther down, a much deeper valley. If you roll a ball into the shallow dip, it will settle there. From the ball's point of view, that is the bottom. It can jiggle around a bit, but unless something gives it a big kick, it will not climb back up the slope and fall into the deeper valley downstream. In classical physics, that would be the end of the story. The ball sits in its little hollow forever. In quantum physics, the rules are stranger. There is a small, but non-zero, probability that the ball can tunnel through the hill between the two dips, appearing suddenly in the deeper valley, without ever climbing over the top in the usual way. The shallow dip, which looked like a stable resting place, turns out to be a false minimum, a false vacuum. Now replace the ball with the fields that fill space, like the Higgs field that gives particles their masses, and the hillside with the potential energy landscape those fields feel. Our universe today may be sitting in a configuration that looks stable over any timescale we can directly experience, yet is not the absolute lowest energy state allowed by the deeper theory. If that is true, then in principle, a tiny region of space could someday fluctuate or tunnel into a more stable configuration, a true vacuum. What would that look like from the inside? Not like an explosion in the usual sense. There would be no shockwave of air, no fireball. Instead, there would be a bubble of new vacuum appearing somewhere, perhaps unimaginably far away, perhaps not, and then expanding at very nearly the speed of light. Inside the bubble, the values of fundamental fields would be different. The Higgs field could settle into a new value. The strengths of forces, the masses of particles, even the structure of atomic nuclei could change. The bubble wall, racing outward, would act as a boundary between two different versions of physics. Outside, our familiar laws. Inside, a new set. Because the wall moves at essentially light speed, no warning can outrun it. There is no way to see it coming in advance, no time to prepare, no strategy to survive the transition. Wherever the bubble passes, the old rules stop and the new rules begin. Depending on the details, the new vacuum might not allow atoms to exist at all. Chemistry, as we know it, could be impossible. The bubble might be a kind of sterile region, where matter exists in much simpler forms. Or perhaps it would permit new kinds of structure we cannot predict. But whatever it is, it would not be a continuation of our world. This sounds like pure science fiction, and yet it arises, uninvited, from very sober calculations. When the Higgs boson was discovered at the Large Hadron Collider in the year 2012, its measured mass turned out to have an interesting implication. Plugging that mass, along with the top quark's mass and other standard model parameters, into the equations that describe how the Higgs field behaves at very high energies, some theorists found that our current vacuum sits precariously close to the boundary between absolute stability and metastability. In many analyses, it appears to be metastable, a very long-lived false vacuum, rather than the true minimum. If those calculations are right, then, in the abstract space of possibilities, our universe could, at some point, undergo a transition to a lower energy vacuum state. The bubble picture is a way of visualizing that transition. Before the anxiety kicks in, it is important to add the next line. The estimated lifetime of such a metastable vacuum, given our best parameters, is stupendously long. Not just longer than the current age of the universe, but longer by factors so huge that they make the evaporation times of black holes look modest. In practical terms, the chance of this happening anywhere in our observable universe in a time remotely relevant to life, stars, or even black holes is effectively zero. In other words, vacuum decay, if it is possible, is not something you lose sleep over. It is less a realistic threat and more a thought experiment with teeth. It reminds us that the apparent solidity of the laws of physics rests on assumptions about the underlying vacuum that might, in principle, be overturned. False vacuum decay is not the only wildcard in town. Dark energy itself, the same component that seems to be driving accelerated expansion, could undergo its own phase transitions. In some models, the field or mechanism that we currently describe as dark energy might change its behavior abruptly after a very long time, switching from a repulsive effect to an attractive one. That could, in principle, halt acceleration and start contraction, eventually producing a big crunch or a bounce into a new expansion. These ideas are cousins of more familiar phase transitions, like water freezing into ice or boiling into steam. In those everyday cases, temperature and pressure changes push a substance from one phase to another. In cosmology, the parameters are different, but the logic is similar. A field trapped in one state might someday find it energetically favorable to reorganize into another, reshaping the large-scale behavior of space-time in the process. This is where popular culture finds fertile ground. Comics and films sometimes show universes resetting after a catastrophic event, timelines rebooting, realities merging or splitting when some mysterious field flips its state. Those stories rarely track the real physics closely, but they borrow the emotional skeleton from ideas like vacuum decay and cosmological phase transitions. The universe, in that storytelling mode, is not a fixed stage, but a dynamic object that can change its rules mid-performance. Within the physics community, opinions about how seriously to take these ultra-long timescale speculations are split. Some cosmologists argue that pushing our equations so far beyond the domain where they have been tested is more of an exercise in imagination than in science. We have never observed vacuum decay. We do not know how quantum field theory and gravity truly mesh at extremely high energies or over stupendous spans of time. It is entirely possible that our current descriptions break down well before such processes become relevant, making detailed forecasts little more than mathematical fan fiction. Others respond that, unsatisfying as it may be, we should follow our best theories wherever they lead, as honestly as we can. If the standard model plus general relativity, with parameters measured in colliders and telescopes, imply that certain events could happen given sufficiently long times, then that implication is part of our current knowledge, whether or not we think it will survive future revolutions. Ignoring the consequences just because they are uncomfortable or hard to test feels, to them, like turning away from the mirror. Both attitudes have a point. When we talk about the universe's end, All of our scenarios involve extrapolations across dozens of orders of magnitude beyond where our theories have been directly verified. We use general relativity, which has been exquisitely tested in solar systems, binary pulsars, and gravitational wave events, to speak about the behavior of space-time over scales that dwarf our horizon. We use quantum field theory, grounded in collider experiments, to talk about vacuum stability on timescales that make those experiments look instantaneous. Wildcards like vacuum decay and dark energy phase transitions serve as reminders of that audacity. They tell us that the question, "How will it end?" is not only about distant phenomena, but also about the limits of our own frameworks. From one angle, that can feel unsettling. It means that the futures we draw, heat death, big rip, big crunch, bounces, aeons are sketches made with tools that may themselves be provisional. From another angle, it is a source of humility. The universe is under no obligation to conform to our tidy categories of endings. It may have resources we have not imagined, constraints we have not glimpsed, subtleties in its vacuum structure and field content that will only come into view with future physics. Still, even a provisional map is better than none. If heat death is the slow fade ending, written in the steady climb of entropy and the thinning of structure, then vacuum decay and similar processes are the trapdoors hidden under the carpet. They are less likely, as far as we currently understand. They are difficult to test, but they cannot be ruled out completely, and that, perhaps, is the deepest lesson they offer. The end of the universe, whatever form it takes, is not just a destination out there in time. It is a test of how far our understanding can stretch before it breaks. When understanding runs up against its own limits, something very old in us wakes up and starts drawing circles instead of lines. We do not like final endings. We tolerate them in short stories and seasons of a show, but when it comes to the world itself, most cultures reach instinctively for cycles. Days return, seasons loop around, generations follow one another. In some philosophies, even individual lives are not truly finished, but feed into new births, new chances. It is not surprising that cosmology, once it learned to talk about beginnings and endings at all, almost immediately began to ask whether the universe might, in some deeper sense, go around and come back again. One of the simplest ways to imagine that is to revisit the Big Crunch, not as a brick wall, but as a doorway. In the old recollapsing picture, the universe expands from a hot, dense state, cools and thins as it grows, then eventually slows, stops, and reverses. Galaxies fall back toward one another. Temperatures climb, densities rise. At the end, everything is squeezed into an incredibly compressed, fiery phase, often described as a singularity. If you take that singularity seriously as a real boundary, the story ends there. But you can also ask a different question. What if the collapse does not terminate in a simple, unphysical point of infinite density? What if, instead, quantum gravity, the as-yet unfinished theory that should unify general relativity and quantum mechanics, softens the singularity and replaces it with a bounce? In that case, the Big Crunch could be followed by a new Big Bang. The universe might oscillate, in some form, through cycles of expansion and contraction. In such a big bounce scenario, each cycle might, in principle, start with slightly different conditions. Quantum fluctuations at the bounce could seed new patterns, the distribution of matter, the values of certain fields, perhaps even some effective constants, could shift slightly from cycle to cycle. Our universe, in that view, would be one episode in a longer series, separated from others by violent but finite transitions. This is already a big leap from our everyday intuition, but some thinkers have gone further still. Among them is Roger Penrose, who proposed what he calls conformal cyclic cosmology, or CCC. In CCC, the cycles are not expansions and contractions in the usual sense. Instead, each universe-long era is called an aeon, and the aeons follow one another in a more subtle way. The idea rests on a piece of mathematics called conformal geometry, which cares about angles and shapes, but not about absolute size. Picture the very far future of a universe in which all mass has effectively disappeared. Black holes have evaporated. Protons, if they decay, are gone. What remains is radiation. Massless particles like photons streaming through an ever-expanding space. In such a world, the concept of scale starts to lose meaning. Without masses, there are no natural clocks or rulers. Only the pattern of light cones and the angles between trajectories matter. Penrose's bold move is to say, if scale no longer matters at the end of an aeon, then we can mathematically rescale that infinite, cold, radiation-filled future so that it looks, in the right variables, like a hot, dense beginning. In conformal geometry, the infinite future boundary of one eon can be mapped onto the Big Bang surface of the next. In this way, the end and the beginning can be identified, not in our usual, physical sense of time, but in a transformed, scale-free picture. In CCC, our universe is one aeon among many. Before our Big Bang, there was the remote, cooled future of a previous aeon. After our far future, there will be another aeon, whose hot start is conformally related to our cold end. The cycles here are not expansions and contractions in ordinary time, but chains of eons stitched together in a higher-level geometry. Penrose has even suggested that events in the aeon before ours might leave faint fingerprints in our cosmic microwave background. In particular, he and collaborators have claimed to see concentric circles in the temperature fluctuations of the background radiation patterns they interpret as possible remnants of black hole collisions in the previous aeon, whose gravitational effects could leak through the conformal boundary into our Big Bang. These claims are controversial. Other groups have reanalyzed the same data and argued that the circles are statistical flukes, artifacts of how the maps are processed, or features that can arise by chance in standard cosmological models. The debate has not been resolved in favor of CCC. For now, most cosmologists treat conformal cyclic cosmology as an intriguing, beautiful proposal with a highly speculative, observational toehold, not as an established theory. CCC is not the only cyclic idea on the table. There are ekpyrotic models, whose name comes from an ancient Greek word for conflagration. In these scenarios, our Big Bang was not the absolute beginning, but the result of a collision between higher dimensional branes extended objects that live in a space with more than 3 spatial dimensions. The geometry of the branes and their motion can, in some models, generate repeated bangs as branes approach and collide again and again over very long intervals. Loop quantum cosmology, an offshoot of loop quantum gravity, offers yet another version. In those models, the grainy, discrete structure of spacetime at the smallest scales can effectively repel at extremely high densities, preventing singularities. A contracting universe might bounce into a new expansion when the density reaches a critical value determined by the underlying quantum geometry. Again, the result is a kind of cycle. Contraction, bounce, expansion, perhaps followed by another contraction. All of these models share a common emotional thread. They refuse to grant endings the last word. Instead of a single, final heat death or crunch, they offer an endless chain of transformations. The universe does not die, it recycles. It sheds one set of conditions and takes on another. It creates, erases, and recreates structure, perhaps forever. Popular stories about cosmic rebirth rarely cite these theories by name, but you can feel their influence in the culture. The final act of the film Interstellar, where a character falls into a black hole and passes through a region that seems to transcend ordinary space and time, then emerges into a new configuration, plays with the idea that singularities might connect to other domains. The closing sequence of the film 2001, A Space Odyssey, with its journey through a stargate and the birth of the so-called Star Child, has a similar flavor. These scenes are not meant as literal depictions of CCC or brain collisions, but they resonate with the notion that going through a cosmic extreme might lead not to nothingness, but to another state of being. Here, it is important to draw a careful line. When physicists talk about our universe giving birth to another one, whether through a bounce at high density, or through a baby universe branching off inside a black hole, or through some other mechanism, they are talking about regions of space-time that are, in all reasonable models, causally sealed off from us. Once a new universe budded off, there would be no way to send a signal back, no tunnel we could navigate to migrate from parent to child. The boundary conditions and causal structure make these realms separate in a very strict sense. So even if our universe were part of a larger multiverse, or part of a sequence of aeons, it would not mean that we, as observers within this particular space-time, get to ride the wave into the next one. From our perspective, an end is still an end. Cosmic rebirth, in most of these models, is about what physics allows beyond our horizon, not about personal or civilizational escape routes. From the standpoint of evidence, it is also crucial to be clear. As of now, there is no observational confirmation that our universe is cyclic. The standard, single-bang, ever-expanding model with or without a late-time heat death is simpler and fits the data we have very well. Ekpyrotic scenarios, loop quantum cosmology bounces. All of these sit at the frontier where mathematical imagination pushes ahead of direct tests. That does not make them worthless. On the contrary, they are valuable in at least two ways. First, they show us that our current picture of a universe with one beginning and one end is not the only one compatible with known physics. There are consistent frameworks in which time stretches on indefinitely, organized into segments that look, from the inside, like individual universes. Second, they sharpen the questions we ask of the data. If a theory predicts circles in the cosmic microwave background, or a specific pattern in gravitational waves, then those predictions can be hunted for and, if not found, used to constrain or rule out the theory. In the end, the question, what comes after the universe ends, may not have a single answer. It might branch, depending on which aspect of after you emphasize. One possibility is to say nothing in any meaningful sense. If the universe drifts toward heat death, with no phase transitions or bounces, then after a certain point, there are no gradients, no structures, no observers. Time, as a parameter in the equations, keeps going, but there is no narrative left. Asking what comes after is like asking what comes after the last frame of a film when the projector keeps running on a blank strip. Another possibility is a catastrophic stop. In a big rip, the scale factor blows up in a finite time. In a true, unsoftened big crunch, densities and curvatures diverge. In those cases, the question, what comes after, may be ill-posed, because our theories themselves break down at the endpoint. Without a reliable description of physics beyond the singularity or beyond the rip, it may simply be that there is no well-defined continuation. The third possibility is a handoff to something else that we will never see, but that physics allows us to sketch. An aeon following our aeon, a baby universe branching from our collapsing core. A new expansion phase triggered by quantum gravity effects. From the point of view of a larger, perhaps timeless structure, these might be steps in an unending process. From our point of view, they are endings that happen to be connected to other beginnings across a gap we cannot cross. Standing under the night sky, all of this is invisible. The stars do not tell you whether they are part of a one-off story or a recurring chapter in a cosmic cycle. The data we can gather from our small patch of space-time, as powerful as it is, may never be enough to settle the question completely. But the fact that physics can even articulate these options, that it can make room for heat death, for rips and crunches, and for rebirths we will never witness, is already a kind of answer. It tells us that after is not a single, simple concept. It can mean nothing. It can mean a sharp stop, or it can mean beyond our reach. Once you admit that after the universe might mean nothing, or something we can never reach, another, quieter question moves into the foreground. What does any of this do to the way we live inside the part of the story we actually get? So far, we have been watching from a long distance. Galaxies fading, black holes evaporating, abstract curves on graphs. But the reason these images grip us is not just scientific curiosity. It is because somewhere behind them there is the smaller, more personal worry. If stars go out, if entropy wins, what happens to ideas like purpose, progress, hope? Life, at the most basic level, is a way of riding gradients. A plant takes the gradient between sunlight and darkness, between carbon dioxide in the air and sugars in its cells, and turns it into growth. An animal uses chemical gradients in food and electrical gradients across membranes to move, to sense, to think. A civilization uses gradients between hot and cold, high and low, ordered and disordered, to power factories, computers, telescopes, stories. In physics language, you need free energy and low entropy to do work. Not just energy in some undifferentiated sense, but energy that is arranged in such a way that it can be harnessed. A room full of air at a uniform temperature contains plenty of internal energy, but you cannot run a turbine from it without a hotter or colder reservoir to push against. The capacity to build, to act, to maintain complex structure comes from those differences. That means that every cosmic ending we have talked about so far can be translated into a statement about the breakdown of gradients. In a heat-death universe, the problem is slow exhaustion. Over immense timescales, nuclear fuel is spent, gravitational wells are flattened by evaporation, temperature differences even out. There is still energy, but it is spread too evenly to be used. The gradients that living systems depend on are gone. In a big rip, the problem is violence. The accelerating expansion grows so strong that it tears apart bound structures at every scale. Even before free energy is fully spent, the scaffolding that could have used it is shredded. No star, no planet, no molecule survives to take advantage of whatever gradients remain. In vacuum decay, the problem is rewriting. A bubble of new vacuum sweeps across space, and the rules that make chemistry possible, particle masses, coupling strengths, the stability of atoms, may simply change. The gradients life uses are not just flattened or torn. They are replaced by a new landscape that may not support anything like life at all. Seen from that angle, the universe's possible ends are also the ends of certain kinds of stories. Not because they are morally aimed at us, but because they close the window in which complexity can be maintained. Physicists have not been entirely content to leave it there. In the 1970s, Freeman Dyson wrote a famous paper with a quietly provocative title, Time Without End. In it, he asked whether an extremely advanced civilization could, in principle, stretch its subjective experience indefinitely in an ever-expanding universe, even as physical resources declined. The idea, very roughly, was this. Suppose you can slow your thinking arbitrarily. If you space out your moments of consciousness more and more, and use less and less energy per thought, you might, in theory, fit an infinite number of thoughts into a finite total energy budget. An immortal, extremely patient network of minds might arrange its computations and wakeful periods so that, from its own internal perspective, time goes on forever, even as the external universe cools and thins. It is a beautiful, slightly haunting image, consciousness retreating, strobing ever more slowly in the dark, eking out eternity in a universe sliding toward heat death. Later work, however, was less forgiving. More detailed analyses, taking into account the details of cosmological expansion, the temperature of the background, and limits from thermodynamics, suggested that even such strategies hit hard ceilings. There are only so many computations you can perform per unit of free energy. There are limits to how cold your environment can get, while still allowing certain processes to run. In many of the models that best fit our current universe, those limits rule out the infinite subjective survival Dyson imagined. You can stretch your story. You cannot make it endless. This pattern repeats. Whenever we imagine ways for life to outlast cosmic constraints, the universe responds with rules. Interstellar, the film about a desperate attempt to leave a dying Earth, gives us a close-up version of this tension. In that story, dust storms and crop failures make the planet increasingly uninhabitable. The solution? or at least the hope, is to find other worlds around distant stars and move there. It is a very human response. When one garden fails, find another. From the perspective of long-term cosmology, though, every planet is temporary. Even if you spread out across the galaxy, then to other galaxies, building habitats around long-lived red dwarfs and mining white dwarfs and neutron stars for residual heat, you are still surfing a wave whose energy will eventually dissipate. There is no planet, no clever engineering trick, that can decouple you entirely from the slow shutdown of free energy in the universe. At best, you ride the front of the wave for as long as the laws of physics allow. You do not outrun the ocean. You could call this the lesson of cosmic mortality. Just as an individual's awareness is framed by birth and death, any civilization's story is framed by the lifespan of the gradients it depends on. Our usual sense of progress, more knowledge, more control, more reach, quietly assumes an open future, an indefinite runway. Cosmology whispers that the runway is, in fact, finite, even if it is unimaginably long by human standards. Reactions to that whisper vary. Some people find it despairing. If everything we build will eventually be ground down by entropy, if all records will be erased, if even black holes will evaporate and return their energy to a featureless bath of radiation, what is the point? Why build cathedrals that will crumble, archives that will fade, instruments that will fall silent? Others find it strangely liberating. If the universe does not offer us cosmic permanence, then the meaning of what we do cannot be measured by how long it lasts on an absolute timeline. It has to be measured in more local terms, in the experiences of conscious beings while they are conscious, in the patterns of relationship and understanding that exist for a finite stretch and then do not. The fact that something is temporary does not make it trivial. If anything, for some philosophies, it makes it more precious. Think of a piece of music. The value of a symphony is not lessened by the fact that it ends. Its beauty is bound up with its finiteness. The moments inside it are meaningful because they are part of a pattern that unfolds and completes. No one asks what the song is doing a million years after it is over. On cosmic scales, heat death does not erase the fact that for a long while, the universe hosted structures as intricate as galaxies and as delicate as brains. It does not retroactively cancel the existence of art, of kindness, of discovery. Those things happen. They are real. The fact that, in the far future, no one will be around to remember them does not change their reality in the moments when they occur. Physics adds another subtle layer. Information, in some sense, may persist even when the structures we care about have dissolved. The detailed patterns of matter and energy in a person, a planet, a galaxy, are imprinted, however faintly, in the distribution of particles and radiation that follow. Correlations, entanglements, tiny imprints in background fields, all of these carry echoes of what once was. In quantum theory, there is even a strong principle that information is never truly destroyed, only transformed and dispersed. But whether that counts as survival is not a question physics can answer. If the atoms that once made a poem are scattered into intergalactic space, and the exact arrangement of their motions is, in principle, encoded in the phase of a passing photon, does that mean the poem still exists? Most of us would say no. The pattern that made it a poem has been lost in any practical sense. The fact that some ghostly mathematical correlation remains is interesting, but it is not comfort in any human way. The difference between erased forever and scrambled beyond retrieval is a philosophical distinction more than an emotional one. Our stories have been circling these questions for a long time. Apocalyptic science fiction, from old disaster novels to modern films about asteroid impacts or runaway climate change, often uses the end of the world as a way to ask what matters when the future is suddenly short. Quiet dramas, where a single person faces a terminal diagnosis, ask the same thing on a smaller scale. Even works that play with cosmic imagery, like the ending of the film Melancholia or the final pages of certain existential novels, are often less about the literal destruction they depict and more about the tension between wanting closure and fearing it. Cosmic endings give that tension its widest possible frame. They say, not only you, not only your culture, but everything you can imagine is temporary. Then they wait to see what you do with that information. One response is denial. To insist, explicitly or implicitly, that there must be some escape hatch, another realm where meaning is stored permanently, another cycle where the same players return, a cosmic archive where every moment is kept. Another response is acceptance, sometimes tinged with gratitude. To say, the universe is temporary, and so am I, and that is enough. The fact that we get any chapter at all is the improbable part. Physics does not tell us which response is correct. It only draws the boundary conditions more clearly. Whatever the universe does in the deep future, we still wake up tomorrow, within our own thin slice of cosmic time. We still make choices. We still care about people. We still step outside, on some clear night, and look at the sky, feeling something that is not easily reduced to thermodynamic gradients. The end of the cosmos is not a countdown timer for human meaning. It is a distant context, so distant that all of recorded history is a flicker within a single frame that can, if we let it, sharpen the way we live now. Once you accept that meaning has to be made locally, inside a brief and fragile window, there is still something almost absurd about the next step we take as a species. We try to sketch the edges of the window itself. By any reasonable standard, predicting the end of the universe is an outrageous thing for small primates on a single planet to attempt. We invented agriculture only a few thousand years ago. We have had telescopes for a few centuries. For most of our history, the night sky was a dome of unknowable lights. And yet, sitting at computers and mountaintop observatories, we now write papers that calmly discuss what might happen in time so long that we have to stack powers of 10 on top of one another just to write them down in a compact way. The audacity would be unbearable if it were not also backed by something real. We are not guessing entirely in the dark. We have tools. The first of those tools is observation. The story began to sharpen on a mountain above Los Angeles in the late 1920s. Working at Mount Wilson Observatory, Edwin Hubble compared the spectra of distant galaxies with their apparent distances and saw a pattern. Almost all of them were receding from us. And the farther away they were, the faster they seemed to recede. In 1929, he published what is now called Hubble's Law, the first clear evidence that the universe is expanding. That single plot of recession velocity against distance was a hinge. It turned the universe from a static backdrop into a dynamical system. If everything is moving apart now, then at earlier times everything must have been closer together. The past stopped being an infinite stretch of sameness and became a story with a denser, hotter beginning. Once you accept that, it becomes natural to ask about the future evolution as well. In the mid-1960s, another accidental discovery added depth to the picture. Arno Penzias and Robert Wilson, working with a radio antenna in New Jersey, picked up a persistent background hiss that they could not get rid of. They cleaned pigeon droppings from the instrument. They checked for equipment problems. The signal remained. At almost the same time, a group at Princeton realized that what they were seeing matched a prediction. A uniform bath of microwave radiation left over from a hot early universe. In 1965, the cosmic microwave background moved from theory to data. Later, space missions such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and finally Planck, in the early years of the 21st century, mapped this background in exquisite detail. The final set of cosmological parameters from Planck, released in 2018, did more than tell us the age of the universe with impressive precision. They gave us a detailed breakdown of its contents and geometry, how much ordinary matter, how much dark matter, how much dark energy, how curved or flat space is on the largest scales. Those measurements, combined with galaxy surveys and other data, let cosmologists fit models of the universe's expansion history. And once you have a reasonably well-constrained model for how the expansion behaves as a function of time, you can run it both backward and forward. You can say, within some uncertainty, this is how the universe has changed up to now, and if the same ingredients and equations keep applying, this is how it will continue to change. That if is important, but so is the fact that we can make the statement at all. The late 1990s supernova work added another, more surprising piece. Two competing teams, the Supernova Cosmology Project and the High Z Supernova Search Team, spent years painstakingly finding and measuring distant Type 1, a supernovae, the kind that can serve as relatively standard candles. They had to account for dust, for host galaxy properties, for subtle biases in which events get detected. It was slow, often frustrating work. When the data finally stacked up, the pattern was unavoidable. The distant supernovae were dimmer than they should have been in a decelerating universe. The expansion was speeding up. That realization did not appear overnight as a bolt of revelation. It crept in through error bars and reanalyses, through conference talks where people cautiously said, "It looks like," and through long arguments over whether some overlooked systematic effect might be fooling everyone. By the time the discovery was widely accepted and labeled Breakthrough of the Year, it had already passed through years of skepticism. That is worth remembering when we casually say, "The universe is accelerating," and then proceed to draw diagrams of its far future. Those diagrams rest on a stack of careful, fallible human labor. Alongside observation, theory has been doing its own quiet work. General relativity, Einstein's theory of gravity, tells us how matter and energy curve space-time, and how that curvature guides the motion of matter and light. When you apply those equations to a homogeneous, isotropic universe, you get the Friedmann equations, which connect the expansion rate to the densities of different components: matter, radiation, curvature, and whatever acts like dark energy. Quantum field theory, the framework that underlies the standard model of particle physics, tells us about vacuum fluctuations, particle masses, and the behavior of fields like the Higgs. It is in that framework that Hawking-derived black hole evaporation, that we talk about vacuum stability and false vacua, that we estimate the properties of the very early universe. Thermodynamics, and in particular the second law, gives us the language of entropy and free energy that we have used to talk about heat death. It tells us that, absent external inputs, isolated systems evolve towards states, with more microstates per macrostate, fewer useful gradients, less capacity to do work. These three pillars, relativity, quantum field theory, thermodynamics, are not perfect. We know that general relativity, for all its successes, cannot be the final word, because it predicts singularities where it cannot describe what happens. We know that quantum field theory, as currently formulated, struggles with gravity and with some infinities that have to be tamed by renormalization tricks. We know that our thermodynamic reasoning, while robust in many contexts, can be subtle when applied to the universe as a whole. Yet together, they form a framework that has survived an enormous number of tests. Black holes behave as general relativity predicts, at least outside their horizons. Particle physics experiments at colliders match quantum field theory calculations with astonishing accuracy. Thermodynamic principles underlie technologies from engines to semiconductors. When cosmologists use these theories to extrapolate toward 10 to the power of 67-year black hole evaporation times or 10 to the power of 100-year heat death estimates, they are extending them far beyond the regimes where they have been directly tested. But they are not inventing from scratch. They are stretching known tools and being honest about the stretch. The stretching continues today. The James Webb Space Telescope, launched in late 2021 and beginning science operations in 2022, looks deeper into space and therefore farther back in time than many previous instruments. It is already finding surprisingly mature galaxies at epochs when, according to earlier models, structure should have been in its infancy. Those findings do not overthrow the basic framework, but they do force adjustments. They remind us that the universe's capacity to surprise did not end with the discovery of expansion or of dark energy. Other projects, such as the Dark Energy Survey, the Dark Energy Spectroscopic Instrument, and future missions, like Euclid and the Nancy Grace Roman Space Telescope, are mapping the distribution of galaxies and the bending of light by gravity over vast volumes. Their goal is to trace how structure has grown over cosmic time and, in doing so, refine our understanding of how dark energy behaves. Every time astronomy improves its instruments, the universe has, so far, turned out to be weirder than our earlier, simpler models assumed. Once, we thought the Milky Way was the entire universe. Better telescopes revealed other galaxies and the expansion between them. Once, we thought black holes were perhaps mathematical curiosities. Better radio and X-ray observations, and eventually gravitational wave detections, showed that they are common, active, and sometimes violently merging. Once, we thought most of the universe's mass was in stars and gas. Better rotation curve measurements and lensing maps forced us to invent dark matter. Once, we assumed that expansion would slow. Better supernova data told us it is speeding up. It would be naive to think that this pattern has stopped. Our predictions about the far future of the cosmos are part of this same process. They are likely to be corrected, refined, perhaps radically revised as our observations and theories improve. That does not make them meaningless. It means they carry an implicit footnote based on what we know now. There is a tension at the heart of all this. We are using laws of nature that have been shaped and tested over a few centuries in a tiny corner of space and time to say something about cosmic histories spanning trillions of years and beyond. We are fitting models to data from one observable universe, one realization of whatever the underlying physics allows, and then extrapolating those models into regions where we will never have direct evidence. Some people see that and conclude that such predictions are little more than stories. Others see it as a triumph of human reasoning, that we can say anything non-trivial about those regimes at all. The truth probably lies somewhere in between. Our models are not arbitrary. They are anchored in data and constrained by mathematical consistency. But they are also not sacred. They are sketches, to be updated when contradictions appear. One of the healthiest signs that cosmology is a living science, not a dogma, is the presence of disagreement. Physicists argue, sometimes fiercely, over the nature of dark energy, over whether conformal cyclic cosmology deserves serious attention, over how to interpret the Hubble tension, over whether certain anomalies in the cosmic microwave background are meaningful or noise. These disagreements are not symptoms of failure. They are part of how knowledge moves. If everyone agreed too quickly about the universe's fate, that might be a reason to worry. So when we ask, how will the universe end? What we are really doing is balancing two things at once. On one side, we have telescopes, satellites, detectors, and equations that have given us a remarkably coherent, quantitatively successful picture of the cosmos from fractions of a second after its hot beginning to billions of years into its current expansion. On the other side, we have the recognition that our picture is partial, provisional, and drawn by creatures whose entire history is a tiny blip on the timeline they are trying to chart. The question of the universe's end is, in that sense, as much about the limits of knowledge as it is about cosmic timelines. The story of our attempts to answer it, the inventions, the mistakes, the corrections, the stubbornness that drives people to spend careers chasing tiny signals in noisy data, is itself one of the more interesting threads in the universe's own unfolding. By now, the question of how the universe ends sounds less like a line in a documentary and more like a quiet pressure that has been building underneath everything we have talked about. We began with a simple observational shock. Early in the 20th century, in the year 1929, Edwin Hubble showed that distant galaxies are receding from us, that space itself is stretching. The universe is not a static backdrop. It has a past. It has a trajectory. Later, in the mid-1960s, the discovery of the cosmic microwave background turned that trajectory into a story with a hot, dense opening chapter. A faint hiss of microwave light, washing over Earth from every direction, told us that the universe was once something very different from what we see now. Into that picture, we brought the second law of thermodynamics, entropy, the arrow of time. We watched a cup of coffee cool on a table and saw, hidden in that mundane scene, the same principle that drives stars, galaxies, and eventually whole eras of cosmic history toward configurations with less usable difference. The universe, it seemed, is a wound-up system running down. From there, we followed the timeline outward. The Stelliferous Era, this age of starlight that we take for granted, emerged as a brief window in which nuclear fusion writes intricate stories in the sky. We watched stars live, swell, collapse. We saw them become white dwarfs, neutron stars, black holes. We let the camera drift forward to an imagined graveyard universe where the bright beacons are mostly gone and compact remnants dominate the landscape. Then we let the black holes, which once looked eternal, grow old. In the mid-1970s, Stephen Hawking took quantum field theory and general relativity and showed in that quietly radical 1974 paper that black holes should radiate. Hawking radiation turned the ultimate one-way traps into very slow leaks. Given enough time, even they evaporate. On top of that, in the late 1990s, came the discovery that the expansion of the universe is accelerating. Those distant Type 1, a supernovae, dimmer than expected, forced us to introduce dark energy, a component that fills space with a gentle, repulsive pressure. Suddenly, the old contest between eternal expansion and eventual recollapse had a new player. Heat death in an ever-expanding universe became the default outcome, at least if dark energy behaves like a cosmological constant. Big Rip scenarios and modified dark energy models added more violent possibilities. Big Crunch and Big Bounce stories shifted from favorite textbook endings to more speculative side notes. Along the way, we opened trapdoors, false vacuum decay, phase changes, baby universes, conformal cyclic cosmology, with its chain of eons stitched together by conformal geometry, ekpyrotic brain collisions, quantum gravity bounces. None of these are established. All of them remind us that the space of possible endings and rebirths is larger than the narrow corridor our current data has illuminated. Underneath all the physics, three questions have been waiting the whole time, steady and simple. Does the universe end at all? If it does, how does that ending unfold? And if there is any sense in which something comes after, what could that possibly mean? For each of those, we have told the best stories science can offer right now. They are not final verdicts. For the first question, the honest answer is that we do not know. In one sense, the universe may never end as an object in equations. Space-time could keep expanding, coordinates could continue, radiation could thin but never quite vanish. In another, more human sense, there may come a time when no new stories can happen, when no gradients remain, when the universe still exists but narrative is impossible. Whether you call that an end is partly a matter of language. For the second question, our best guess at this moment leans towards some form of heat death. A universe in which dark energy keeps driving expansion, star formation fades, structure thins, black holes evaporate, and everything simple and complex is dissolved into a cold, dilute bath of low-energy quanta. But that guess sits on assumptions about dark energy that might shift with better observations, and on theories of gravity and quantum fields that we know are incomplete. A small change in the equation that describes dark energy could bend the whole curve of the future differently. For the third question, about what, if anything, comes after, we have even less ground to stand on. We can outline three broad categories. Perhaps nothing, in any meaningful sense, follows a terminal heat death. Perhaps there is a catastrophic stop, a rip or a crunch or a vacuum transition where our equations themselves fail to continue. Perhaps, beyond what we can access, there is a handoff to another eon, another universe, another branch, causally severed from ours. Beyond that, we have only metaphors and the willingness or unwillingness to imagine. Within a single human lifetime, our picture of all this has already changed more than once. A person born before the mid-1960s has lived through the discovery of the cosmic microwave background, the rise of precision cosmology, the shock of Hawking radiation, the shock of cosmic acceleration. The idea that the universe might end in a slow, cold drift rather than a fiery collapse is only a little older, culturally, than the internet. Conformal cyclic cosmology. Big Rip doomsdays. Vacuum metastability linked to Higgs measurements. These are all very recent arrivals. It would be arrogant to assume the flow of surprises has stopped. So instead of a neat conclusion, what we really have is an unfinished answer and a chance to notice how the question itself feels now, compared to when you first heard it. Do you feel smaller, as if the scales and times we have walked through have stripped away some illusion of centrality? Do you feel oddly calmer, because the distances are so vast that everything you love is safely buried within them? Do you feel a little more anxious, now that you have a vocabulary for endings you did not know how to name? Do you feel strangely comforted by the thought that even the universe has a kind of mortality? There is no correct reaction. The science is one thing, the way it resonates with your own story is another. There is, however, another answer available to us, one that does not depend on picking a favorite fate. Maybe the important thing is not whether the universe ends in a whisper of cold photons, in a tearing of space, in a crunch and a bounce, or in an endless chain of aeons. Maybe the important thing is that, for a brief period within whatever this whole structure is, there exist beings who can notice that there is a story at all. Beings who can look up, infer the past, model the future, and feel something about it. Imagine the night sky again. Perhaps the same mental image you carried from the beginning. A familiar pattern of stars. Perhaps Orion. Perhaps the band of the Milky Way. Perhaps just a handful of bright points over a dark city. Now overlay, softly, what you know. Each star is a temporary flame in a larger thermodynamic drama. Its light left long ago crosses space, enters your eye, stirs electric patterns in your brain. Every part of that chain is finite, contingent, fragile. And yet, in this moment, it is real. No scenario we have discussed, no heat death, no big rip, no cosmic cycle can reach back through time and undo the fact that right now, in this tiny patch of space-time, awareness exists. Curiosity exists. The act of listening to a story about the end of the universe exists. These are not cancelled by future entropy. They are part of what the universe has already done. That may be as close to closure as science can honestly give. Any strong, definitive claim about what comes after the universe ends would be less physics and more theology or speculative metaphysics. What we have drawn instead is a map of plausible futures, based on the best tools we currently have, marked with uncertainties and open questions. So, the last image is simple, and it is not an answer. Maybe, far beyond any time we can emotionally grasp, the universe really does end in a thin, cold murmur of radiation, stretched across a darkness too wide to picture. Maybe it ends in a sudden, bright tearing of everything apart. Maybe it hands off, quietly, to another aeon that will write its own histories under new rules. For us, here, the practical question is smaller and harder at the same time. Knowing that everything around us is temporary on some timescale, how do we choose to live inside this chapter? Whatever you decide, that decision, too, becomes part of the universe's brief, unfinished answer to itself.